I'm thinking maybe you can hear me now. Today's gonna go. Can you hear me now? I think yes. Okay, good. I think we're off to a new start here. Okay, good, good, good. Sorry about the delay, but yes, I think all the hardware chaos of last week, I think I have conquered. Hold on. I mean, I'm behind, but bear with me. I think we're going to be good today. Thank you for your patience. I will say hello properly in a moment. I'm still thinking that you could still hear me, but now I'm bringing up the board. As soon as the board is here and assures me that fixed. Excited for a class that might actually work. Just a week and 2 more minutes to be true. Hold on. All right, so we're almost there. We're almost there. I did see you, Josh, by the way. Thank you. That counted. Thank you. Hold on. I'm gonna say hello. I know there were people in the chat. We're 4 minutes late. All right. Oh, good afternoon. Okay, yes. So first of all, hello, Nathan. Thank you for responding before. And I'm still, please do continue to confirm. I think you can still hear me. I'm thinking that. And actually, in a minute, if someone wants to use their voice to confirm whether I can hear you, that would be good also. But hello, Nathan, and thank you. Hello, Carla, and thank you. Good afternoon, Madonna, and thank you. Oh, and Madonna, thank you for the feedback. Okay. Also, good afternoon, Josh, because I saw you. Thank you. Okay. Hi. Oh, and here we go. All right, now we're rolling. All right. Good afternoon, Carla. There's Josh again.
Good afternoon.
Oh, and that was voice, and I really needed that today. Thank you. That was Angela, I think. Thank you. Excellent.
Yes.
Awesome. Thank you. Okay, that helped on a lot of levels because yeah. So good afternoon, Carla. Good afternoon, Josh. Hi, Montserrat. Oh, and that was voice too. He just like triple dip. It was like a hat trick. All right, awesome.
The Thursday has been good, Professor.
Sorry.
The Thursday has been good.
Yes, thank you. How about you? Yeah, well, I'm good enough that at least I have hardware now. Yes. How about yours?
Good.
That's good. That's good. Oh, but I hear you. Oh, all of you. Wait a minute. You're in the. I don't mean to get us off the. I'm not where you guys are right now, but I hear there's major. Did you all? If you're here at all, wait. What am I trying to say? I hear there were major subway issues today. I know that in fact lab was canceled for a different set. So I hope you're all okay and you haven't had too stressful a day. Like the A and C were down and stuff. I don't know. Hello, Mira. Okay, but thank you for asking, Josh. Okay, and hello, Antigone. Oh, and Antigone. Wait a minute. Thought you're here. Thank you for. Okay, I don't mean to get personal, but thank you for being here. I think I'm pleasantly surprised. Pleasantly.
Yep, I'm here.
Okay.
Physics lecture. I'm here.
Okay, well, that's awesome. Wait, I don't get personal. We could talk for 2 seconds, like after class. But am I crazy to think that I got an email from you? Am I confusing? Did I get an email from? We could talk right after
No,
class.
you did, but it was regarding lab.
Oh, okay.
That was me. Yeah.
Well, all right. Well, I hope you're okay. Okay, I won't get. But thank you. That's very responsible of you. Okay. Cool. Great to see you. Okay. Anyway, all right. Anyway, so, and hello, Mira, if I didn't say so, who else is here? So hello, Alirat, hello, Caitlin, hello, let's see, oh, someone else is here. We will start, and I remember my promise from last time. We were going to get straight to, and hello, Amelie, hello, Michael, hello, Alex, I think that's, hello, Taco Rub, okay, that is pretty much everybody. Okay. Good afternoon, excellent. All right, we're going to get rolling in a second. Just, you'll note, as you know, as I saw that there was no hello, hi, Taco Root. All right, I'm just going to get straight to it because I remember last time we had a number of discussions that I did find very productive, even though challenged by hardware and so forth. But I also, if I remember correctly, and I feel, I've been in correspondence with your lab instructor and so forth. If I remember correctly, the one thing that last time we did not get to. Now, correct me if I'm wrong, but I believe that last time we never really got to talking about homework 1B, which is a big homework and a big deal. And I think that my promise was that we would get straight to that this time, that we would make that the priority before, even if we don't discuss anything about your labs. So if that's correct, if I'm remembering correctly, that the main thing people want to see is homework 1B, then that's exactly what we're going to do. And don't worry. And I will say it's good for us to do that right now because the issues that come up in homework 1B permeate for the rest of the semester. So I can assure you of this, even if it's certainly not too late for us to talk about it. We're going to deal with these issues of what is ultimately known as harmonic oscillation. We're going to deal with them big time for many weeks. We'll put them on the table now. As you know, because of stuff, your next homework wasn't due today. It's due next week. Hopefully by the time we finish today, you'll feel in a position to be able to do that. The other thing is, just as we keep going, you'll notice if you ever did hand in homework 1B on time, your points are just sort of slowly escalating as we progress until the moment where we fully have gone over it and I fully give feedback on your thing and then really tell you if you have a perfect score, if there's still a couple of things you need to tweak or not. I still haven't done that. But until I do, your points just keep going up to show that the ball's still in my court. Anyway, I hope you understand that. Okay. All right. So I'm looking at the chat and then hi. I saw that. Okay. So unless you correct me, well, we're going to go straight to homework 1B right now. I'm going to walk through it using the 5-step method. I don't believe we've started it at all. Please stop me if I'm wrong about that. But what I'm going to do is literally do it as though I'm you. Like this is like a solutions manual. I'm going to be we're not going to do this every time with every single homework, but this one, yes. So, wait, I'm going to say, there's something in the chat. Hold on. I think it's a good question. Hold on. No. Now, good question. This is partly why we're here. Someone privately in the chat is saying, do we lose points if we don't complete the homework? You don't lose points if you don't complete the homework. But you don't get all of the points until you do complete the homework. That sounds like a contradiction, maybe. What I'm saying is this, especially here where I haven't even gone over it yet, there is still a chance for everybody, like everybody still could revise or add to their homework, or they could still finish things that they did not try yet. You can still complete the homework 1B. It is not too late for anybody. And once you do complete it, you can get all the points, even if some of your answers are wrong. Okay, so let me be I know we still don't, this is still all new to everybody. Yes, to get all the points, you do need to complete the homework. That is true. But it's not too late to do that, number one. Number two, if say you submit a draft where the homework is incomplete, well, right, you won't get all the points, but you're not losing points because you could still get them later. That's the sense in which maybe you want to think of all these points as like extra credit in a way. They're points to be gained. They're not there's no penalties, but yes, you won't get all the points until you complete the homework, but you still can. And you can use whatever knowledge you get from this class in order to do so. That is not cheating. And that's partly why I haven't even scrutinized, partly why I'm also behind, but I haven't even penned it. I haven't even marked anybody's homework yet, because it's totally fair and legal if anybody wants to adjust their homework based on what I start saying in this class today. But people have gotten a lot of points already just as an acknowledgement that they've definitely tried and they've done a lot already, even without my help. So, okay, long answer, I know. But the really I'm really trying to say is you definitely don't lose points for wrong answers. I'll say that. It is quite possible to get full credit on a homework with a bunch of answers being wrong. What you get points for is doing all the steps of the 5-step process. Okay, I see there's more in chat. I'll look in a second, but since we're about to finally dive into this portion of the course, you get points for doing all the steps of a 5-step process on any given problem in a homework or in an exam, which is like really what we're practicing for with the homeworks. Okay, so what I'm about to do right now, after I look back in the chat, I'm about to start for the first time, I know 3 weeks into the course, I'm about to start walking through what I would consider to be a 5-step solution to each of these questions in the homework. I'm going to show you what it would mean for you to do the thing that would get you all the points. That's what I'm going to do right now. If you didn't exactly do this yet, that's okay. That's why I'm showing you now. But you're always supposed to make an attempt before I go over it, and that's why like the points keep going. So everything is a draft. You do a draft, you get some points, then you do more, you get more points. I look more closely, you get more points. It's just a back and forth all the time. I mean, I'm over talking this, but I really do want to make it clear that it's all about the process and the drafting and the steps. It's not about right answers, and it's not really about strict deadlines. It really isn't until an exam. With exam, the deadline is strict. But with these homeworks, it's a back and forth, a back and forth. So, okay, I'm going to look at, I don't know if that just made things more, but it'll be more clear when I start going over this right now. And again, anything I do right now, you can use to revise your homework if you find out that you did it all wrong. Last thing on that too, though, don't remove anything you already have done for your homework. Anything you've already done is great because you've already done work, and that's why you're getting credit. Even if you find out you think it's wrong, please don't remove the document. That for 1,000 reasons, don't. If you want to put in a new document and say, please ignore my old document and just look at this new one, fine. It's like, fine. I mean, it makes my life easier. But the more work you show, the more documents that are up there, the more you just look like an amazing scholar. So don't remove old work, even if you think it's wrong. Okay, I'm going to now look in the chat. Yeah. So now, okay, so there's something in the chat. You're going to show you this. Okay, I'm not trying to stall, but so, and also there's a new thing in the direct chat. The old person, not the old person, grandma, the person that just asked me that in the direct chat, if you would get a moment to like acknowledge in the direct chat whether I did actually answer your question, that would be really great. And you get points for that. Okay, great. Wait, isn't that two? Is that two different people though? That's weird. Okay, well, thank you. Okay, awesome. That's awesome, but why is it under? All right, anyway, great, thank you. So the other person that just asked in the direct chat, and now I'll move on. Someone just asked in the direct chat, does it mean that if our aunt, both, so I did answer. Okay, yeah, so I answered both of you. Okay, right. So again, yeah, guys, like yes, you get partial credit. It's not about the right answers. It's about the steps. Really, the reason I'm almost laughing, I'm not laughing. That's a very legitimate question. But when you start seeing how this works, at least with me, you'll see it's like not even partial credit. It's like credit. Like the credit you're getting is for doing the steps. That's the credit you get. And when you lose credit, it's for not doing the steps. The answers, honestly, the answers are going to fall. If you literally do the steps, the answers are going to fall into place. But if you do every bit of work and you do the whole thing and you show what your final answer is, yeah, if your final answer isn't right, that's like the least of your troubles. You will lose very little if that's the only thing that goes wrong. Okay, I'm going to start now. I think we're all good. Okay. So, and again, I'm going to take it from these questions in the chat that I'm going to start drawing this, but give me a show of hands or something in the chat just to confirm that I'm correct, that we're about to go over. We are about to go over homework 1B, finally. Homework 1B in spring. That is what we're about to go over. I'm about to go over it from the start. So again, what I'm doing now on this whiteboard, which of course I'll upload to you as a PDF, this whiteboard is you now, okay? Like this is literally what I'm looking for, like that you would give me or that you already did give me, right? i.e. it's a blank sheet or a blank set of sheets. It's a blank file. It's not my paper with the questions. This is like a blue book, right? You took my questions. They're like an exam booklet to your side. Now you're creating a fresh document with your fresh work as though it were an exam, because again, all of this kind of is just practice for the exam. So the first thing you're going to do on your sheet is you're going to let someone in from the waiting room. You're going to provide a diagram. I happen to have given you a diagram. So your diagram is going to look a lot like my diagram. It probably will look a lot, but you're still going to do your own. You're not going to copy paste my diagram for 1,000 reasons. You're just going to make a diagram. You're also going to note that in a lot of questions I ask in the future in homework or on exams, I don't always provide a diagram, but you do either way. So this one, you had the sort of luxury that you could sort of copy mine, fine. So here's the diagram. This is step one of the 5-step problem solving process. Step one that we all always do first is and again, tell me, I think I explained this last time, but maybe in the chat, tell me, I don't remember if I literally explained this 5-step process or not. I'm going to walk you through it now, but I will tell you it is definitely a sheet for this, a 1-pager for this 5-step problem solving process is under tools in it's under tools in the Google Classroom. Like there's a sheet that outlines this. Step 1 is DF. Put in the chat, did I at all talk about the 5-step process or not yet?
You talked very briefly, Professor, but not like in depth, if that makes sense.
That totally makes sense. Okay, no, that's perfect. So I mentioned it, but I didn't spell it out yet. In other words, like I haven't told you like what the steps are. In other words, is that correct? Is that what you're saying? Like,
I think you may have went through the steps, but I don't know how in depth. Unless that was in depth enough, I'm not sure.
okay, no, fair enough.
It was like really, it was like late first class, I believe.
Okay, all right, fair enough. All right, okay, all right. I'll totally take that. That is helpful. Thank you. That's also major points. Okay, all right. So here's my step 1. Step one, DFP means diagram and fact pattern. Okay. Now on your homework, I'm not saying you have to spell out diagram. You don't. I'm writing in red. Wherever I write in red is me telling you as the teacher. Okay. In your homework or in your exam, you certainly can to the side labels. This is step 1. I would recommend it. I would recommend keeping track of the steps. You could say step 1, diagram and fact pattern, or step 1, DFP. But now I'm telling you as a teacher, that means diagram and fact pattern. So the first thing you do, whether the problem did it or not, is you're providing a diagram. Now again, here's where I'm expanding. Like I honestly, like as Josh just mentioned, I'm expanding now on purpose for like the one big time I'm going to all semester. So I would recommend to those of you who are paying attention, like, here's where you might want to take some notes that I'm not necessarily writing down because I don't want to confuse the document, But by diagram and fact pattern, by diagram, first of all, I don't necessarily mean graph. I don't necessarily mean free body diagram. I don't necessarily mean vector diagram. I don't necessarily mean a solution tool diagram. I don't mean a diagram that we make to help us figure something out. That comes later. What I mean is literally is a picture of the situations, of the facts, because all physics problems first start with a scenario. They start with facts on the ground, like here is the experiment, or here's the research phenomenon, or whatever, right? So we're diagramming that. We're laying down what the facts are that are presented to us. And here's the key thing. If I were to write anything down in my notes right now, this is what I would write, even though I'm like deliberately not going to write it on the whiteboard. You'll know a diagram is complete. You will know a diagram is complete when every single letter, i.e., every single variable or constant that you're going to use in your math appears as a label in the diagram. That's like the key point. I'll say it again. Like, you'll know your diagram is done when every single variable and constant that you're going to use in your solution in the mathematics, when every single letter that appears in the mathematics appears here first as a label in the diagram. Like what and again, if you ever want me to repeat something, you can tell I'm happy to repeat. But so put it in the chat if you didn't catch that, if you want me to say it again. Of course, also this is all on the video, but and someone's here. What I'm really trying to say, and I'm telling you the things that they all sound like kindergarten, but I did not come to realize these things until like seriously out of graduate school twice and teaching already for 15 years. Like I didn't realize the real purpose. So I always knew they wanted a diagram, but I kind of thought it was always just like kind of give a rough sketch of like my mind. I kind of thought it was always just kind of a rough thing. I didn't realize the real purpose of the diagram is you're defining terms in the diagram. You're literally, these labels that you see right here, K, M, X, and X naught, the fact that those are labels in the picture, what we're really secretly doing is saying from here on in, when I use M or I use K in my equations, this is what I freaking mean. That's like, I'm in, okay? It's like if any of you does computer coding or old fashioned computer code, it's kind of like we're saying, let M be this. So now from now on, we all have an idea of what we mean by M, okay? So the purpose of the diagram is first and foremost to use labeling to define your terms. That's what's happening. Okay, and you'll notice my labels here because we're getting into advanced physics now eventually. Like, we're not in physics 101 anymore, we're in physics 102. So you notice, first and foremost, my labels are letters, because I'm going to be doing some like abstract mathematics. I'm going to be figuring out some things in general. I'm figuring out how springs and masses in general in the universe behave. So really, at the core of this, I don't really care how big m is or not. Whatever my solution is going to be should work for any m, right? But then, because we're being concrete, and this happens to be an actual experiment or based on an actual experiment, or whatever, so then it does turn out that I do have some numerical facts. So I include those in my fact pattern. Like, this is all still part of step one. I write down, as you were told in the problem, n happens here to equal 0.3 kilograms. K happens to equal, here in this context, 200 newtons per meter. And x naught, the initial displacement from equilibrium, happens to equal 0.15 meters, right? And x equals 0. Notice x, I think I mentioned this last time. Again, stop me if I didn't. We distinguish in physics between triple equal signs and double equal signs. More people here, sorry. Okay. Triple equal signs. I'm also going to change the view on the screen. Sorry. If I didn't say this before, I'm saying it now. Triple equal sign means equal by definition. Double equal sign means equal by circumstance or discovery. Triple equal signs are different. They're stronger than double equal signs. If something's equal by definition, first of all, then we know it's always true. If it's true at all, it's always true. That's very powerful. That's very reliable. As opposed to double equal signs, which often are kind of true, but not as strictly. But also, if it's a triple equal sign, then we're never trying to rack our brains for like, wait, what experiment did this come from? Or like, under what cases is this true? We're like, no, we're just saying, we're declaring it to be true. It's a language shortcut. So x triple equal sign 0 means that spot. So actually, I'll even write it right here, just to be clear once and for all. When we say x equals 0, means the equilibrium, the equilibrium position with spring edge. I think that's all clear to you now that you've had like 3 labs on this, but right, that x equals 0 is what we're deciding to call the 0 spot. Wherever the edge of the spring would have been had we not been jamming a mass on it and pulling it on purpose, right? If not subjected to any external forces, wherever the edge of the spring would naturally sit and rest, that's what we call in English equilibrium, and that's what we declare mathematically to be the center of our coordinate system, 0. Oh, so last thing in our diagram, and in fact, this is something that we've got to put in that actually is not in the sheet. So in this diagram as well, we label our coordinate systems. If that's 0, that x equals 0 spot is 0, then I'm going to decide that anything to the right is positive, the left of that 0 is negative, and I'm labeling that coordinate system. Could I have made a different choice? I could have, but what I couldn't do is not make a choice at all. I have to choose what is positive and what is negative, like what is right or left, positive or negative. And whatever I choose, I'm declaring it as a label in my diagram, and then I'm going to stick with that consistently throughout. Okay, so this is step 1 DFP. Again, I'm going to say, because now we're getting into, like, these are things I'm not flexible about, for whatever reason. So I'm going to say also firmly, this is what we call step 1 DFP. Again, you have to do it for any problem, especially exam problem that you have. These are the requirements of it. What was I just going to say? So what you cannot do, you can't copy and paste my diagram. It's not that that's cheating. It's just that it defeats the purpose. Like, you have to go through it yourself. You can use a computer. I'm not saying you have to use a pen, but you have to recreate your own diagram. Even if you think you're just literally mentally copying what I did, fine. But the act of doing that, you'd be amazed, still forces your brain to decide what to include and what not to include, and what's important and what's not important. Even if you think you are just mentally copying a picture that I happen to give you, fine, but I'm not always going to give you one. And trust me, that act is different from hitting Control Z, or you know what I mean? Like from hitting Control C and Control V, you know what I'm saying? Okay, so that's, or command, whatever. All right, so that's step one. We've done step one, DFP. Now, step two. Stop me if I'm being unclear at all. Step two is WIQ. What is, everybody always leaves out. It's the easiest step to do if you remember to do it. And it's, in a weird way, the most important step. It really is, especially for real physics research or science research. Like, you gotta right away tell people why we're here. Why have we gathered here? What is the research curiosity, or etc. Right? So you now, in your terms, you have to spell out, and I'm talking now question one on the sheet. Right now on question, and again, we're not copying and pasting. We're literally forcing our brain to distill what is the crucial information that's being asked about here, and what's just a distractor. You might have noticed I use way too many words to make any kind of point at all. Have you noticed that? I speak a lot and I say very little. I know, it's crazy. Well, same thing in the homeworks, right? Question one, I use a lot. Now, of course, I don't think I'm doing that when I do. I'm not consciously trying to confuse anybody, but I use a lot of words to get at the point of question one. Your job is to distill that down and show that you know exactly what the question is and you're not distracted by anything else. And the more you can do that symbolically and concisely, the better. So, for example, what you would do in question one is you might write just something like this. Like, I know I have all this English, but you would say something like, at x equals x naught, and again, correct me if I'm wrong, but I believe that is what the question is. I believe I ask something like, at the initial position of 15 centimeters from equilibrium or whatever, like, what is the force? What's the magnitude of, determine the force exerted by the spring onto the mass, right? So this is the question. At the position x equals x naught, what is the F? Notice, last thing, distillation of the question, it's in your words, not mine. They might be very similar to mine, but sort of ideally they won't be. But also notice there's a condition chucked into that question. You might, if you're taking notes right now, you might want to write in your notes that generally speaking, the question begins with some kind of condition. Like this one does. Like the question isn't just what's F. Because as we're going to see very quickly in this problem, like that can be the F is different at different places and at different times. So the question here is, assuming x equals x naught, what's F? Okay, so that's the question, and you must write it down. I'm gonna stall one more. I can't even. This is so ridiculously important. This step, it's so preposterously important, especially given how easy it is. I should never say nothing is easy. Nothing is easy. Life is hard, but it's not. It's a very important step to do. And 99 times out of 100, when people don't do it, it's just because they're not doing it, not because they tried and they failed. But here's an example now. Someone was a couple people were asking in the chat, like, do we lose points if we don't complete the homework? Like, so here's where you're getting points, is by doing these steps that I'm telling you right now. And all of this is in preparation for the exam. My real goal here today, and my real goal, if we go over a couple more homeworks, my real goal is to make it to have it 100% clear between you and me exactly what I'd be looking for when you solve problems on the exam. I want that not to be a mystery when we get there. I actually want the exams to be easy for you. Like, I know we talked about that before. They're not supposed to be tricks. They're supposed to just be a clear, like, recitation of practices or principles that we've practiced. Okay. And this 5-step method is the principle that we're practicing. So what I'm getting at is this 5-step method is the grading rubric. It is the grading rubric. If we were, for homework and exams, if we were taking an exam right now, I'm sorry, if you just handed an exam to me and I asked this problem or on the exam, right? Like, I would be looking at your work. And literally, if I looked at the diagram and then you started answering the question right now, which people do all the time, you just like started diving in because you can already see the answer in your head, which I know a lot of you can. If you already saw the answer well, this is the sample paper. Sorry. This is the sample that I'm making for you right now. Like this will be the sample of how to, this is a sample. Sorry, not to, but I just saw something in the direct chat. Very fair question. Someone's asking, is there a sample paper? All right, this PDF, when I upload it, will be the most expansive, detailed, clear sample of how you solve problems in this class that I could give you. And I'm not saying that sarcastically, like that's like a very fair question. But that's why I'm doing this walkthrough. That's why today, in fact, I'm like willing to be a little bit more boring than it, because I just want to really be clear. This will be the sample. And to be even more clear, I mean, it's a sample of how you do homework and how you do exams. And to be even more clear, it's why I'm saying a lot of sidebars that I'm asking you to write down as sidebars in your notes, but I'm not putting them on the paper because I want the paper, this PDF, just to be the clean, literal demonstration of what a sample of what you would do for me. Okay, so and maybe let me know in the chat if I answered that. But what I'm saying to you all now about grading and stuff is like right here at this stage. I know there's people, maybe many of you are maybe bored to tears because you already know what the answer is to this question. You can see it in your mind. I know that, and you should be proud of yourselves. I'm not mocking that at all. But say you already see the answer in your mind. That's a good thing for 1,000 reasons. But if you just start writing that right now, if it were an exam, what right now I would do on the paper is you would see, I would write like -2 WIQ. That would literally be my grading thing. I would take, if you skip this step for good or for bad, I would literally say -2, and I would expect by the time we got to the exam that you would, and I would just write WIQ. And by then I would expect that you know what I mean. I'm saying, what's the question? What's the question? And again, I have 1,000, that may seem unfair and ridiculous. I don't ultimately think it is, but I'll try to explain why later. But for right now, I'm going to say that's how the grading works. You're looking to do the steps, and you get all the points as long as you do the steps. And whatever steps are missing, you lose points for. So by the time we get to the answer, as long as you've done all the steps, you probably have gotten you will have gotten most of the points. And if you've really done the steps right, you probably are going to get the right answer. But okay, so anyway, so the good news is you get tons of points even if you don't have a right answer. The bad news is if you don't do the work, I don't care how good the answer is. Okay, I think we're all, so maybe the person in the chat that asked me about sample, maybe let me know if that's clear or not, but I'm going to go on now. So I'm saying this is step 2. What is the question? Okay, and I believe this is the question. So now we go to step 3. Do too to make this super clear. I'm even going to say, whenever I'm writing these words here, I'm putting them in brackets. I'm not saying you have to write that in your sample. You just write step 1 DFP. That's good enough. Or step 1. That's good enough. You don't have. But I'm writing these because so that you could see. Okay. How to. All right. Step 3. So step 3. Okay. All right, so this is step 3 now. Notice we haven't done a lick of like algebra or like computation at all yet. Step 3, we're going to write down things that we know to be true, but things that we know to be true in the universe in general, even before this problem began. Like or what we call principles. This is where we write down ultimately things that I would call equations, right? Real equations. Some of you might call formulas. I don't really like the word formula. We'll get into that at some point. But this is the place where you write down those kinds of things. Now, and I'm going to do that in 1 second. But notice now that we're really breaking this down. I know if you all got this far in science, if you already at this point, I know you've been through a lot of like science and math class and a lot of word problems. And you've been in a lot of situations where people tell you to show your work and stuff like that. And you probably remember, a lot of you, that like even in 7th grade or something, when you first got algebra word problems or something, people would always say, oh, well, people might have often said things like, first write down what you know, then write down what you need to figure out, and then let's start doing algebra and go from one to the other or something. I think that's right. That is right. But that I think the reason people get into a lot of trouble with that, the reason that sounds easy, but then people somehow fall apart when the problem gets hard enough is to say to people, write down what you know, totally like leaves out the fact that there's two very different types of knowledge that we're ever dealing with in science, in physics in particular. There's two types of knowledge, at least, just like there's two types of equal signs. Okay, there's things that we know from definition, and there's things that we know from discovery or from observation, right? That's like the two different types of equal signs. Similarly, here in a problem, there's things that we know because the problem told us so, that we already wrote down in step one. The things that we know to be particular to the problem, particular facts that we know, those we write down in step one. Those just set the table and say, here's the situation. And then step two, we say, what are we wondering about this situation? Now in step three, we're going to say, well, what did we already know before we encountered this situation? What knowledge were we walking around with in our brains about the universe in general that might possibly have any help or bearing on the situation? That's a totally different type of, in other words, laws, principles, and definitions. So the example of the one that I think we really need here, to finally cut to it, the law that I think I need here is called Hooke's law, which of course, you all established in lab one. Like I'm going to operate now with the confidence that you kind of understand this law now, or you remember it, or you were refreshed on it in lab one. We know like this, right? And again, please in the chat, tell me if there's anything about that law that's like still making you uncomfortable. There would be no shame in that. There would be a lot of shame in pretending you're fine with it if you're not. But I think it's something we know, and it's a law, right? And notice the problem didn't tell me that. It's not only true because of this problem, it's true before this problem, right? Okay, so I write that down. Oh, good. Oh, that's fair, very fair. And I totally understand why you, okay, fair enough. So someone in the direct tab is saying, well, what do the variables stand for? Okay. Well, I'm not sure if I should put this on the whiteboard or just tell you, but so F stands for force. I'll write it here, hold on. F stands for force. It's the force exerted by the spring onto the mass at any given position or any given displacement from equilibrium known as X. The F stands for force. X stands for displacement from equilibrium, as in the diagram, and K stands for stiffness of the spring. Now, I might want to, depending on what other people feel about that, I may want to break that down further. Like, I don't want to gloss over this, but the quick answer to your question is F stands for force, X stands for equilibrium. No, it's sorry. F stands for force, X stands for displacement from equilibrium, like how far out the mass is from the center. And K, which is maybe the most subtle part of this, K stands for how stiff or strong the spring is. Okay, hold on one second. I want to, well, hold on one second. Here's my story. Well, first of all, I want to ask the person that asked in the direct chat, very fair. Please remember that if one person has the guts to ask something like that in direct chat, it's got to be the case that at least 3 other people what's going to ask it. And it probably means that 5 other people needed it to be asked, but don't even know that they needed it to be asked, okay? So first of all, the person who put that in the direct chat should like be proud and should submit for points and all that. But second of all, then the person that put that in the direct chat who asked what the variables stand for, please do, and I really mean this seriously, because this is the kind of thing where I could go down, I could go deeper if that's what's helpful to the class, or I should be careful and not go down a rabbit hole. So I at least want to hear from that person whether I sort of answered his or her question. But I'm also going to say to the rest of y'all, I'm going to say, look, one person just asked, what do the variables stand for? That signals to me that some of you might need to hear more about this law. Some of you might not. So basically, what am I going to do? I'm going to go with whoever gives me whatever feedback. Like, I can go whatever speed. You guys need to control me, right? I'm the car, but you're the driver. Like, seriously. So I'm going to go on right now if I don't hear from anybody, but like, you should take this opportunity. Some of you in the direct chat could either say, no, we do get it. Like, that's that person's issue. Like, we're fine. I think, fine. It's in the direct chat. No one's going to be offended. You could say to me, please go on. Or you could say to me, no, actually, F equals negative kx is still totally unclear to me. But if no one says anything, I'm going on. But wait, but I'm actually nervous that nobody's saying. Hold on, I'm going to change if you want to speak. Oh, okay. Someone said say something. Okay. I'm going to accept that. Thank you. Okay. So I'm going to go on. Notice, and I'm trying. This is a little bit of a subtle dance here. Like what I just wrote there in black. Someone else is here. What I just wrote in black is totally reasonable for you to add in your homework or in your exam. Like a GDP absolutely can be and maybe should be often prefaced by a little English. It doesn't. English is good. I'm just saying, if I now get into a whole thing with graphs and everything about exactly what F equals negative kx means, like I could do that as a teacher right now, and I really wouldn't have a problem. But I wouldn't expect. But I'm not putting it on the PDF because, like, I wouldn't expect. This is about the level that I would expect you to give to me. Okay. So again, if this is a sample, this is what the sample would look like. Okay. So we write down F equals negative kx. Pardon me for 1 second. I'm just going to. Okay, so now I'm going to go on to thinking about what to put in your notes. GDP is the next, well, maybe, yeah, notice I haven't plugged or chugged at all yet. Most of us, when we think, oh, the professor wants me to show work, we think they mean they want us to show the plugging and chugging. But a lot of people often will say at a certain level, in fact, almost everybody at some point in physics says, I can solve the problems. My only problem is I don't really know how to start them. But like once someone shows me how to start them, then I can do physics problems, or I can follow what they do in class. Or more likely, what a lot of people say is like, I can do the physics problems as long as you tell me which equations to choose. Then I pretty much know what to do. And like what I'm here to say is, well, that means you can do math. Like ironically, the part that people often are afraid of in physics is the math. Most people actually can do the math. A lot of people say their trouble is they don't know like which equations to choose and stuff like that. That's because in most people's minds, what they mean by doing the work is skipping straight to what I'm now going to call step 4. I'm going to now do step 4, and I'm going to assert that this step 4 that I'm about to do, the key point of it is that 3 steps came before it. Like I can't do this step 4 unless I first did these other 3. These other 3 are the thing that most people skip, which is why by the time they get to step 4, they don't know how to set it up or they don't know what to do when the problem's hard. Now, this problem for many of you might be easy, which is all the more reason then to practice this method here in the context of something that you can see in your mind. So what I'm getting at is if you write down F equals negative kx, even if you don't know what to do with it, even if that's your struggle or in a harder problem becomes your struggle, even if you start getting stuck soon of what to do with it, if it's true, it's true. So you get points for it. Like, honestly, all of these things, these 3 steps that are sort of mindless, which is why they're going to bore some people right now, they're mindless. They're mindless. But each one of them you get points for. F equals negative kx, even if it turns out not to be the perfect equation to use here, even if there's something better that I could do, or should do, it doesn't matter. If F equals negative kx, if it's true, it's true. So I get points for it. So boom. So I've gotten this many points already so far. Now I go to step 4. where you show what we all consider to be showing the work. Only I'm trying to emphasize this is now the work of the particular problem. So in step 3, we wrote down a general truth that's just true in general, f equals negative kx. In step 1, we wrote particular facts down about this situation. And in step 2, we asked the question. So now in step 4, we're going to zoom in. We're going to take our general truth and we're going to make it relevant. Okay, I'm going to take a risk here because this is so important. I'm going to write something down I'm going to keep it in red. So the idea here behind the step method, the whole idea behind the step method is it seems stupid and pointless if you already know the answer to a question. It seems stupid and pointless if you already know the answer to a question. But it's crucial if you don't already know the answer to a question. And the only way that the 5-step method works for questions that you don't already know the answer is if you've practiced it in situations where you do know the answer. Okay, so what? Okay, wait, I'm looking at the chat. Hold on a second. Yeah. So right. Like someone's very goodly asking in the chat on our homework and in the exam, like, should we provide a short explanation along with our math? The bottom line, yes. That's sort of what this 5-step method is trying to force you to do. Absolutely. Every move you make, the more you can explain it, absolutely. And I mean, especially in exams, that's really what we're looking for. Yes. The goal of any one of these problems or anything on the exam, the goal is not to get the answer. You're going to find by the time we get to the exams that I will have given you half the answers anyway. And the other half are like on the internet and it's an open book exam. So the answers are out there. The goal is to prove why the answers are true and to prove that you understand why the answers are true. So yes, the more you can explain every step as you go, absolutely, please, yes, that is the idea. So note this, I'm just going to say this now about PAW. The whole goal here is to do something that doesn't seem intuitive. Well, anyway, the whole goal here is to proceed from true relevant, not other way around. I'm just to say this, you can put this in your side notes or whatever. I'm saying, this is all in preparation for when questions are hard. If you've ever encountered a hard question on a science exam or a math exam or physics exam, if you've ever encountered a hard question where it made you nervous and you didn't know what to do, and you're like, I mean, maybe that's never happened to any of you, but it has certainly happened to me. If I hit a question that makes me nervous and I'm like, I'm not even like, not only do I not know what the answer is, but like, this is like a long word problem and I'm not even sure, like, I don't even know what I should do to get the answer. I'm not even sure I know totally what this question's asking. Now, again, I don't know if you've had that. I've had that experience many times. It's very stressful. What I have found is that what we tend to do as good people, as smart people, when we hit questions that cause stress or anxiety, what successful science students tend to do when we're panicking, we tend to try to go from relevant to true. I'm not consciously. I don't think you've ever. I doubt if you've ever thought it through like that consciously. But what we tend to do, if you really think about it, is we tend to go, all right, what's the professor looking for? Like what? Oh, this is supposed to be a question on like calories and kilojoules. So this is like a question about chapter 2. So he's looking or she's looking for like me to show that I know what's in chapter 2. So all right, so it's like, I guess like the 4.18 calorie to joule conversion is probably relevant here, right? And all that's fair. Like it's all totally human. I'm not mocking anybody. But what tends to happen is we tend to go into like hyperdrive of what's relevant. So we start writing down things that we think are relevant, and we start writing down things that we think maybe the professor wants or whatever, all honorable, all sympathetic. And then we start doing algebra, or we start doing like equation manipulations to try to turn our relevant information into some kind of true, correct answer. And I'm telling you, that's what we all do. And the reason we do it is it's actually, I'm glad at least one person, thank you. At least one person is like finding this relatable. No, I'm good because I know I'm like totally just yelling about it. But yes, the reason we all do that is because it actually sounds like it makes sense. Like it almost does make sense. Like if you didn't have any other option, why wouldn't you do that, right? It's the natural thing to do. What I'm here to tell you is the unnatural thing to do, which is actually correct. Like what actually separates success from disappointment among smart people, like the ability to get over that psychological hump and actually trust a different process. The different unnatural process is not to try to move from relevant to truth, because the truth, you can't turn, no matter how relevant something is, you can't turn it into something true if it ain't true. Like you can't. What we're supposed to be doing is starting off with truth and then zooming in and making it relevant. That's a big difference. And it requires like calmness and like confidence and a lot of practice to do that. And that's why I know I'm over time, and I'm anything but calm, as you can see. But what I'm trying to do with all of this, even if it takes me 2.5 hours, I'm trying to back up to sort of comparatively unstressful questions and break down the actual correct thing that the mind actually does when it's calm, break that down for you, and then give you an algorithm or a script to follow when your mind needs one, when it's not calm. Like in other words, well, so I'm going to show you what I'm saying now. So the big lesson I'm saying here is don't try to go from relevant to true. Try to go from true to relevant, which means first we write down f equals negative kx. That's just freaking true. Even if I don't know what to do with it, even if I don't, of course it's vaguely relevant, like it's topical, but it doesn't answer anything. It's just true, f equals negative kx. Then in step 4, hello, oh, God, I'm screaming so much that Siri and Mrs. Google both like want to know how they can help me. They're like, how can I help? I'm like, well, do you know a good therapist? Okay, step 4, what we now do is we signal that we're in step 4. We're now getting into the particular details of this particular problem, right? Particular application and work. And we write something like here, what here means here in this problem now, right? Like K equals 200 newtons per meter, X equals 0.15 meters, right? Like, so this is where the plugging and chugging come in that everybody's familiar with. So now I turn the page. So I go, so if you like, every time I use the word here, I mean specifically now, I'm like in double equal sign land rather than triple equal sign land. So I write, okay, so here F equals negative, and I put in the numbers carefully with the units. Right. So now I'm doing the work. Now, again, this problem is fairly straightforward. I know that. I'm deliberately dragging out something that for some of you, you just saw instantly in your head. I'm going to address that in a minute. But there's my step 4. I do the work. I mean, in this case, it was only one step. You can imagine that the thicker these problems get, the longer step 4 becomes. But there's my step for this. So I'm going to go on now. Then I'm going to make a big point at the end. So now I go on to step 5. Final answer. Literally, so I'm as you see, I'm going to put the final answer now. It's going to be complete. It's going to be circled. By circled, I mean you got to circle it or highlight it or boldface it. But somehow, you absolutely, especially on an exam, you have to make it clear that it's not just information, but it is literally a landing spot. Like, I used to think this was so kindergarten-y, honestly. I used to actually hate I thought it was like so lame when teachers asked for, like, come on, don't you know what the answer is, teach? I mean, what? But no. You have to show the world not only the answer, but you got to show the world that you know that's the answer. Like, for research, this is vital. Like, it's a I'm not going to overtalk it, but you've got to make it clear that you know this is the answer. And then that means so maybe write this in your notes. Your answer has to be a complete thought. Your answer has to be a complete statement, like one with a subject and a predicate in it. Now, in mathematics, all equations are complete statements. They all have subjects and predicates. It's just that the predicate always is the same. It's is equal to. Right. So what I'm getting at is your final answer is going to be an equation, not a formula, not a definition, not a triple equal sign, a result. Your final answer is going to be a result, as though this was a research paper, which it could be, right? It's going to be a result that specifically ties back to the original question. The original question was, at x equals x naught, what is f equal to? So our final answer is, okay, at x equals x naught, f equals negative 30, like notice the negative sign I kept track of, and I did my units, negative 30 newtons. This is my final answer. I am done now with just question one. Of course, I'm going to go faster on the other questions, okay? This is my sample, but in detail of what it means to do a question. This is the end of question one. I'm still going to make a couple of quick comments here. I'm also going to change a view, and I'm going to breathe maybe someday, and I'm really going to ask you, like, this is almost like a contract too. Like, this is our chance, all of us, to make sure that, sure, thank you. No, I'm glad someone said something. Yes, I mean, yeah, this is definitely our chance to make sure that we're on the same page. I'm risking like boring to tears everybody. I apologize if you're bored, but we want right now, you know, in physics, as always, it's either exciting and confusing or it's clear and boring. Right now, we're going for clear and boring. So, oh God, okay, cool. So the fact that one person just asked me to go back a page at least shows that they are like with me. Thank you. And of course, they can submit for points for that. I'm going to stop and take other questions in a moment. Hopefully there are some, but I'm also going to summarize now a couple of things you might want to write in your notes. Like, so you know, so this is a complete product, right? Like, what, this was just one question, but say the whole homework was just this one question. You know, you would then have, and this was 5 pages, right? You would compile these 5 pages. Maybe you did these on paper, like I would, you know, with a pen, fine. But then you photograph each one, whatever, you know, your iPhone camera, each one of those pages. Then you would compile those pages together into one PDF, preferred ideally, or one Google Doc or something. But you would definitely, and especially if this were an exam, you would to compile all those images into one file, and then you would upload the one file, right? And if there's still questions on how to do that while we're doing homework, please, ask me or ask a friend. We'll help each other. By the time we get to the exam, I don't want there to be any confusion about that. But so you compile these 5 pages into one file, you upload the file, and let's note for a second now, what kind of file did we just upload? Like, if this were the whole homework, the whole standard of this, like, first of all, yes, we showed all of our work. Yes, we followed this whole method that actually, if we really do follow it strictly, the whole idea of the method is it's gonna land us on a correct answer. It's a general method for what to do when you don't know what to do. Like, it's the algorithm for problems where you don't know the algorithm, if that makes sense, right? It's, if you actually get used to following it faithfully, it will guide you to the answer, even in situations where you don't think you know what's going on. Because it's going to like force you to figure out what it is that you don't know what's. Anyway, you follow the method. And when you're done, if you've done it this way, if you've done it correctly like this, one way you'll know that you've actually done what I'm looking for and that you're going to get tons and tons of points, even if, quark forbid, your answer's wrong. The way you'll know you're going to get tons of points is just step back and look at the work and ask yourself, and this is what I want you to write down in your notes, like somehow. Ask yourself, if you gave this paper to someone who did know physics, but wasn't in our class, like wasn't me, if you just gave this to some other physics person and handed it to them, could they mark it up? Could they, or better yet, could they tell you whether they would publish it in their journal? Like, really, even if this is an easy, you know, a comparatively straightforward question, if you think about what we just did, ideally, we just created a paper. We just created a document that said, given a certain physics situation and a given physics question, like, here's our procedure for answering that question, and here's our final answer, right? Like, anybody should be able to follow, anybody who knows physics. I'm not saying you're trying to teach physics to the unwashed masses, but I'm saying if someone knows physics, they should not have to be in our teacher-student context to follow or care about this. In other words, you'll know your homework or your exams are really quality and really what they're supposed to be if you lift them above the level of teacher-student exercise. it starts as a teacher-student exercise, but by the time you're done, it should just be a physics document that literally could stand on its own and just express a physics result to a physics situation that literally could be a physics journal article, except that, okay, presumably this has already been published 400,000 times. Like, you know, a million people have done this already. So maybe it's not original, but it is self-sufficient physics. That is the standard. That's what we're really trying to teach. Ultimately, in Physics 102, remember, we're trying to become in the land of physics research. We're trying to know what to do when we're at the frontier, figuring out something for the first time, something we don't know how to figure out already. We're figuring out something for the first time and then presenting it to the world. This is how you do that. So that's what you want to do. That's your standard for home. And I'm not saying like perfect fonts and perfect, you know, I don't mean literally that it's publication worthy, but I do mean substantively, structurally, you've just invented a self-contained physics derivation, a physics proof. That's what this is. The standard is, could it be read and understand and assessed for quality, graded by someone who knows physics but is not in this class? That's your standard. Okay, so that's point number one. Again, I'll take a breath in a second. I'll move faster to the other questions. But point number two, so point number one is make the work readable by someone, a physicist outside this class. Like that is standard number one. Oh, hey, and sorry, I've got to add. And that means that someone outside this class doesn't need any other documents to read this. I'm sorry, that's really important. Like they should be able to follow and grade your work without looking at the original sheet. I mean, I can't believe I didn't say that. That's like the huge, oh, sorry. All right, I'm going to see what's in the chat. But they should not, and that also means me. If I'm going to grade your work, I should not have to take out my original sheet in order to follow what you're doing. What you're doing has already absorbed and then conveyed all the information of the original sheet. It's a blue book. It's an article. It's not a response to an exercise. Okay? But now there's someone in the chat. Hold on a second. Yeah. Now, okay. So someone in the chat is asking very legitimately, like they say, to be clear, we do these 5 steps for each question. So the clear resounding answer is yes. Yes. Good question. Yes. There's one small exception though, or one thing you'll see in a minute. You'll notice that, so the big answer is yes. When in doubt, the answer is yes. One thing though, you'll notice that most, physics problems start with one big diagram and fact pattern, and then they ask a series of related sort of scaffolded questions about the one fact pattern and diagram. Most physics problems are like that, like a scenario with a bunch of sub questions. So that's true. So therefore, it's true that for each subsequent question I'm about to do now, you'll see in a minute, I'm going to start question 2. I'm going to start by just saying, for diagram and fact pattern, see above. I'm just going to write that, and you can just write that. I'm not literally going to redraw the diagram every time. First of all, yeah, of course that takes too long. And second of all, it's almost confusing because it almost looks like, then am I trying to change things in the diagram or what? So the diagram, you don't have to reproduce every time. You can just say, see above. Okay, but notice even doing that, I'm still acknowledging that step. I'm going to acknowledge every single step, every single time, yes. And please let me know if that answered your question. But, okay, so I'm gonna go on. Oh, okay. Last thing I have to, so I said that my whole number one thing was this has to meet the standard, not in the class. Point number 2, if you're taking notes, which please, I hope you are. And again, remember, if you take anything you write down that I'm saying that I didn't put in this PDF, like if you screenshot it, if I didn't already, I think I literally made a portal specifically for this, but if I didn't, I will. Like for any notes that anybody ever shows me that they took, that I didn't write down, like that warms the cockles of my heart. I mean, that is points. Okay, so here's the second of such a comment is that look, I know a lot of you just saw this answer in your head. I absolutely, and I commend you for it. And I don't want to make you, it's not that I'm trying to take smart people and make them stupider or something like that. And I'm certainly not trying to punish your intelligence. If some of you already saw the answer in your head, that is awesome. But here's what I want to make clear. if you saw the answer in your head right when you started this, and again, and if you just wrote it down, if you just wrote negative 30 newtons in your homework, true, I'm not giving you full credit for that, but that just means I haven't yet. If you didn't do that before, this is not a criticism. Now you know what I'm looking for. Just go back and redo it this way, and you'll get all the points. I hope that is clear. This is all just drafts and drafts until we get to the exam. But here's the advice. Here's the reason for all of this, is that if you saw negative 30 newtons in your head right away, and then so you just wrote it down, what I want to say to you is, yeah, that's awesome. Like, that is how smart you are. But you're really smart. Like, you actually need to give yourself more credit for your intelligence, not less. Like, if you're that smart, it sounds like I'm being sarcastic. I'm not. If you're that on top of things, where you just saw right away, negative 30 newtons is the answer, it's not because something came to you in an uninspired dream. Like Muhammad didn't tell you that. Moses didn't tell you that. It wasn't a flash of random weird spiritual inspiration. And I'm not mocking any of that either. But what it was is that your brain is really fast, right? Please understand, if you feel like you instantly saw that the answer is negative 30 newtons, you didn't actually instantly see that. You very quickly saw that. In other words, for you to know that the answer was negative 30 newtons, what your brain had to do was first recognize that F equals negative kx, and recognize that in this case, k was 200 and x was 0.15, and then your brain multiplied them together. Like, your brain had to acknowledge those three facts and then put them together super quickly for you to see this answer. Your brain didn't skip steps. It just moves them so fast that you got there really fast, which is good. But what my point is, the problem, what I'm really getting at with all this, I don't know why I'm screaming up, because this is what I do. What I'm really trying to say to everybody is, like, we're all super smart even to be in this class. We had to do really hard things even to get here. And I'm no dummy either to have gotten to this job, right? But you know what? Smart people invariably hit a wall at some point if they're challenging themselves properly, and if they're in a hard program, or if they're going to medical school next or whatever. At some point, smart people hit a wall, and the wall is really devastating and anxiety producing and upsetting and often crisis producing for smart people. Because when smart people hit a wall and don't, and I mean, of course, everybody's smart in their own way and all that, but I mean, achieved people like you, people who've been doing hard science, math things for a while, when we get to things that we don't know how to do, what people like us tend to do is go, oh my God, I have no freaking idea. We tend to freeze and go, whoa, what is this craziness? And we either then lash out and get angry at the professor and be like, this is totally unfair. This was not in the book anywhere. What is this not? Or if it's a different kind of situation, we lash at ourselves and we're like, oh my God, I knew I was fooling myself all this time. I knew I was an imposter. I didn't belong here. Like, I knew, oh my God, this program I knew I didn't belong here. I can't handle this program. Like, I'm not cut out for this. What is this? Like, when smart people hit a wall, it's a bad wall, because they suddenly doubt all of their smartness and stuff. I mean, I don't know if any of you can relate to that. Maybe I'm just like yelling into the wind. But what I'm here to say is, be careful of the smart person's wall, and be careful of the breakdown. We all encounter it, especially in these crazy programs that we're in. We all encounter at least one moment where we're like, do I really belong here? And you know why that happens? Because we didn't have enough practice at feeling stupid. Honestly. Like, the problem with seeing things quickly all the time is the minute you don't see something immediately, I tend to think the whole thing is a disaster, because I'm not used to, or I didn't practice the idea of seeing things slowly. So again, maybe I'm only talking to two of you. I don't know. But I know that I started thinking to understand something meant to get it immediately. And I didn't have any, and then when I didn't understand things immediately, I thought either they were crazy or I was crazy. But it turns out that these kind of things that we see really quickly, that's all that's happening, is our mind is flashing through a long movie of steps, and it's flashing through it so fast, we don't think they're steps. We just think they're brilliant insights. So what we're here to do together, and I will stop yelling in a minute and I will go on, but we're here to do together is actually stop and stare at the moments when things are sort of manageable and okay, questions that we think we can answer. We're here to stop and take a mental movie of what our mind just did to figure out a seemingly reasonable thing, and then look at that movie and hold on to that movie, because that's the movie we need to run when things get hard. We don't walk away, we don't panic, we don't say, I don't even know what this question's asking. What we do is we say, let me try to write down what I think this question is asking, right? Let me write down the facts of the question, blah, blah. And then let me just, instead of trying to envision the whole end of the whole road right away, let me just see what kind of equations could possibly relate to this. You get, okay, I'm yelling enough. But I'm just saying, these steps that I just did, I promise you, they are the steps that your mind did. Even if you didn't write them down, we're going to start writing them down now so that we have something to write down when we don't know what to do. Okay, I'm going to move. Okay, I'm going to move on to the next one. I'm sure you want me to move on to the next one. I'm going to look at the time. Could I just get any kind of show? Like, are we clear? Are we still together? Who's still here in the room? Can you just give me an electronic signal if you're even? Thank you, Takaru. Thank you. There's one person in the room. Okay. Just like, thank you, Mira. Thank you, Montserrat. Again, just acknowledge my existence for me, or you're just, if you, thank you, Roland. Thank you, direct chat. Or wait, oh no, that was, thank you, Caitlin. Thank you, Michael. Okay, thank you, all. Oh, he even clapped. See, that was nice of y'all. Okay, still here, Sebastian. Okay, thank you, Sebastian. All right, and I assume all this, and this means I should move out. Hello, Antigone. All right, awesome. Okay, see, I mean, we're all just, remember, I know you think you signed up for physics. It's really group therapy, and it's group therapy for me. I don't know what to tell you. No, all right, good. But it is, because I will tell you this, what makes physics hard is not anything about IQ, or it's all about, it really is all psychological stuff. It's all about confidence and things like that. I am here to say, but okay, so I'm going to go on. Does this mean I can go on to step question? I'm going to start going faster now. I'm going to go to question 2. For a little while, I'm still going to do the steps, but now I'm not going to talk about the steps in its depth. I'm just going to do them, okay? So we're now at step, but stop me again if there's any. Okay, so, but thank you, Madonna. Thank you, Sadie. Thank you, Antigone. Thank you, Sebastian. Thank you, Caitlin. Okay, thank you all. Okay. Two. Here's my step. I'm doing question 2, right? So this is to answer what somebody, I don't, wait, was it public or was it private? It was private. All right, so someone asked in the private chat, like, do you really have to do all the steps each time? Here's my point. For question 2, it's the same freaking diagram and same facts. So I just say, please see above. That's fine. And that's what you do on the exam. Okay, so that's my step 1 of DFP. So now, 2. Right. So the question for this one, and stop me if I'm wrong, but I believe this question is at x equals x naught, right? Again, stop. Maybe can I just get a quick confirmation, and not to be like a teacher, but someone confirm, is that the question for question 2? Like, what is a at x equals x naught? Can anybody confirm? I've lost everybody. Is anybody in the yellow submarine still? Oh my God, I'm totally. This is a long class, isn't it? Could save the ship, someone please. Thank you, Mira. Okay, I gotta open up a new portal for like heroes of the class. Mira just saved the world and saved me from a heart attack. Okay, yes, thank you. All right, so now I'm gonna go to step 3. Thank you, Caitlin. Thank you. And she even checked. Okay, thank you both, Mira and Caitlin. They Victoria today. All right. So step 3, GDP. Okay. I mean, should I oh, and there's Antigone. Thank you. It's almost like she felt a tremor in the emotional universe of me. And she's like, I gotta save this dude. He's going down. He's going down. He needs help. All right. I'm to ask the class now. Okay, I'm not going to put you on the spot. I'm going to say I need a GDP now. Now it's still true. I could write F, F still equals negative kx. That's certainly still true, and it's probably going to be relevant for the rest of the problem. But I think now This question is asking about acceleration. I think it's now directing my attention to need one more big general truth. I'm going to pause and see if anybody wants to put this in the chat. I think there's another law. It's definitely a law. There's a law that you all know from Physics 101 that would be very relevant here. Like, remember, last question we just asked about force. This question is now asking about acceleration. I mean, I think if you're with me, I won't put too much awkwardness, but yes, I will. I think at least two of you in the chat or the private chat could put down a guess as to what equation or law might I write now in order to answer this question. Like, and you've done the homework already, so I think you know. Like, I got the F. I'm looking for the A. What could I possibly write down now? And I'm thinking this is really showing. I know this is not too hard for me, but I think I'm being too boring for everybody. Yes, that's one person. That's awesome. Thank you, one person in the direct chat. Just to torture myself, I'm gonna wait for one more person.
Do force is equal to mass times.
Sorry, what? Sorry, what? Josh said.
You do force is equal to mass times.
I totally agree. Your audio was super cutting in and out, but yes, I'm pretty sure. Maybe I'm. Wait, did you just say F that equals MA? Did you just say? Oh, now I'm seeing in the chat too. I think I'm going to assume you said what I think you said, because now I see three people in the chat. Three people in the chat just said something that warms the cockles of my heart, and I think it's what Josh just said too. I think a bunch of people are oh yes, okay, great, thank you. Okay, I don't know if that's my audio or yours, but yes, thank goodness, thank you for yes. Newton's second law, F net equals ma. Absolutely, yes. Thank you all. Now it's your internet. Okay, it's your internet. Fine. I mean, don't think of it. It's not that your internet is bad. It's that the world is bad. Okay. Let's not blame it on your internet. Okay, but yes, thank you, three people in the direct chat, and thank you, Josh. Yes, I'm going to write this. Notice for the record, I'm not going to go off on a whole tear now. I'm going to try to stick to the subject, but I write it like sigma F equals ma, or I could write it like F net equals ma, but not to be too picky, but I kind of do have to be picky. Like, it's anybody who wrote F equals ma, like, you're saying the right thing, the thing that I was hoping you'd say, and thank you. And what we're talking about here is Newton's second law of motion, yes. But please always remember, because it's pretty important in physics, that it comes up all the time, this law. It's the sum of the forces acting on a mass produce the acceleration of that mass, right? Like, just to make sure we all know, like, this is a general law because it says how forces in general produce accelerations. So if you have any one given object, you add up all the forces acting on that object along a particular axis, like all the forces pushing to the left minus all the forces pushing to the right, and all of them together, like, and you take into account minus signs, and all of them together, you divide by the mass. That produces the acceleration of the mass. Just as a reminder, or as a technicality, but it's a huge technicality. It's add up all the forces in general that are acting on a mass, that will produce its acceleration. So we either say F net, or we say sum of the forces, like sum, like sigma, right? As opposed to just writing F. And the one reason I have to make that technicality, the one reason I have to like remind you of that clarification, all of you, is if we just wrote F equals ma, if I just write F equals ma, that almost starts to look like a contradiction with F equals negative kx. In fact, this is where, honestly, I know from experience, a lot of people are sort of half-consciously confused all the time about all the different equations for F. Like, they sort of don't know which one to choose, or why, or when, or they start setting them equal to each other or something like that. Like, some people will think like, well, we know F equals ma, and we also know this is a spring, so we also know F equals negative kx, so I guess we set them equal to each other. That's not what's really going on. Just for the record, F net equals ma is the law that says whatever forces are acting, plug them all into the left side, and out will come acceleration on the right side. But then what we have is all these separate individual laws that tell us how separate individual forces work. Like, we have a law for springs called Hooke's law that says the spring force does this, negative kx. We have a friction law that says that the friction force does this, mu times the normal. We have different individual force functions. Oh, and we have the force of gravity is negative mg, right? So the idea is that you, in general, draw a free body diagram to see what all the forces are that are acting on an object from all of those different equations, right? Add them all up together to get the net force, and that's what produces MA. I'm just, that's like a quick little review of Physics 101 or something, but just something that in my heart I know really is often still not clear to people in Physics 102. The sum of all the forces equals MA. The individual force acting in this case of a spring is F equals negative kx. And indeed, here, okay. So, and now I'm going to say here, and I think there's things in the chat, which is, I'm glad. I'm going to look in 1 second. Oh, sorry. So now I'm going to go to step 4. You. There is only one force acting horizontally on F. Everything vertically is balanced. We're only interested in the horizontal axis because that's like where the mass is moving back and forth. So here, if I were to draw a free body diagram, I mean, and you could, it would be great credit. If I draw a free body diagram of the mass, there's just this one force on it at any given moment. That's it. So in this case, if I go to add up all of the forces acting on mass, well, yes, in this case, there's only one. So it is negative kx. So in this case, I could say thus here, like negative kx gets plugged in for F net. It's not that F equals F net, like triple equal sign, they're different things. F net means the sum of all the forces. So you plug in all the forces for F net. But okay, here, there's only one. It's negative kx. So negative kx equals MA. Again, this is like a subtle distinction that maybe only really would matter if we had more than one force acting, which like later on we will. So I'm just bringing your attention to it. Since everybody in the chat wrote F equals MA, but they didn't write F net equals MA. So I just want to make sure you were probably just using shorthand, and that's fine. But okay, so that's the deal. So that's my step 4, or we're almost done with my step 4. Almost done with my step 4, but I think there was something in the chat. The chat. All right, so I'm going to go on. So I do that. Now it happens. We already figured out negative kx, like in the last step. It usually goes like this in physics problems. One more step. Hold on. So it's the other side. So to the next page, I say negative kx equals ma. Notice what I'm doing here too. This is another words wise, even for those of you who found this question easy, something I want you to be practicing here for harder questions. Or anyway, however easy or hard you found this question, notice in step 4, you might want to write this in your notes. My habit in step 4 is I postpone the numbers as long as possible. This is another one of those pieces of advice that you won't care about when it comes naturally. And then when it's not coming naturally and you don't want to do it, then you won't want to do it and you won't follow it. And that will be a shame. Possibly. What you want to do is leave the numbers. You want to get in the habit of postponing the numbers as long as possible, doing as much algebra as you can before you plug in numbers. So that, again, this is general physics that you're doing. You're finding out a physics result that doesn't just rely on any one particular value. Also, in case you make computational errors or you're using your calculator wrong or like scientific notation or something's involved, you don't want to get yourself all messed up with an accidental wrong number up here top that then comes carrying down through everything else and like bleeds all over. You the physics, just do as much physics as you can until you plug in numbers. Oh, good question in the chat. Let me get to that in 1 second. I see the question in the chat. Hang on. But so what I'm doing, in other words, I'm going to say like, all right, A equals negative kx over m. right? Like I'm getting A by itself before I even plug in the numbers. I'm getting, so this could be true physics now in general, right? I don't care what values I have, that's true. The acceleration of the mass at that point, or specifically, X is that value of X naught. And then, okay, now I can start plugging in numbers. We already know that the top number from question 1 newtons, and I do see the question in the chat. I'm going to get it in one. So we go like this. I keep track of my units, and then I look like, well, oh, so now I'm going to step 5. Before I get to step 5, so there's a question in the chat about gravity. Okay, so good question. Honestly, if I were really doing a proper free body diagram, so the question in the chat is like, what about gravity? Basically, gravity is certainly there. No question about that. I should put it in my free body diagram. But the thing is, this whole thing is happening horizontally, right? So it's either all happening, presumably on like a lab table. That's the most likely thing. Well, yeah, the most likely thing is this whole thing is happening on a lab table. So the idea is that even though there is the weight of the mass pulling down, presumably there's also the normal force of the table pushing up on the mass, and presumably they are equal and opposite. Not because they always are, but because the way the problem was described, we had a mass that's just free. It's only free to move along the horizontal axis. Nothing is happening. There's no acceleration happening on the vertical axis. So I have good reason to believe that there must be a vertical force balancing or supporting the downward force of gravity. Presumably that's the upward normal force of the table. So you are right. The person who's asking direct shot, really, if I did a proper free body diagram, I should absolutely include that that vertical axis as well. But once I start doing the math of this, when they're asking for, they're asking for the horizontal acceleration of the mass. So I'm only solving for the horizontal acceleration. That's the only acceleration that there is. And therefore, I'm only invoking the horizontal forces. Very fair question, but I sort of hope that answered it. Oh. Yeah, I mean, oh, okay. Oh, good follow-up question. So here's my most honest answer. Oh, yes. If you are complete enough and wise enough to include gravity in your free body diagram, then we must include the normal force as well. Because otherwise, it's going to look like there is some imbalance going, and it's going to look like there is some vertical acceleration that we're going to have to deal with. So yeah, if you're include anything in the vertical, you got to include everything in the vertical. Yes. I will say also that this highlights that maybe the question's not perfect. I want to just look how the original question was phrased. But give me 1 second, because it is a very fair question. Hold on. I just want to see one thing in the original question. In the original question, honestly, and I mean this as a human being, everything the person in direct chat is asking about gravity is totally legitimate and fair, and particularly so because my original question, the question on the sheet, I'm looking at it right now. It says, what is the acceleration of the mass the instant it's released? Honestly, that should really say, what is the horizontal acceleration of the mass? Or have been more super explicit in, oh, well, the diagram does, I forgot the diagram does kind of show that it's on a lab table. I mean, all right, so I'm going to give myself a little credit for that. The diagram does show that it's on a lab table, but I mean, if I were the perfect human being that I will someday be, and when I achieve that perfection, please let my wife know. When I'm the perfect human being that I will someday be, I would have either said, what's the horizontal acceleration of the mass in question 2, and or in the fact pattern, I might have more explicitly said, the mass therefore starts traveling in. I mean, it does say that, traveling in toward the equilibrium position. I might have added the sentence like, it travels in a strictly horizontal direction. And that is then what gives you license to that, plus this diagram that shows a lab table. And there's an arrow there that's showing that it's only moving horizontally. But all of that means that in your free body diagram, yeah, you're good to show gravity, but then you do need to also show that there's a normal force from the lab table balancing the gravity. Very good question. I'm going to move on. No, I'm going to look in the chat. Hold on. I'm going to see a therapist, look in the chat. Okay. So that's my step 4. Yeah, that's my step 4. So now I do step 5. Circled. I say, negative 100 meters per second squared. Now, that's correct. First of all, that's my answer. That's my complete answer. Let's make a couple of comments about that. Oh, wait. Oh, yeah, there's nothing in the chat. Okay. By the way, the person who's been asking these questions in the direct chat, just noted you're being very, very participating today. It's totally noted. It's totally appreciated. These are very legitimate questions. I mean, it's not only one person, but all of you who are. I'm looking at the chat and I'm like, wow, there's quite a variety of people saying things, and I really do appreciate it. And they're all legitimate things. Okay, and Antigone and Josh are showing videos, so I think I'm gonna give them an Academy Award when we're done. Oh, except I'm on strike. Oh wait, I'm not a writer. Okay. Final answer. A couple of things to notice. First of all, notice that I did track units while I did my step 4. I track units because ultimately, like everything else in science, the more you do believe in units and come to rely on them, the more they actually are a help. Of course, like everything in science, just like this method, at first, they're just like an annoying thing that professors are like asking you to do that get in the way of your thinking. But like everything else, it turns out that they aid your thinking once you get to a certain level. So like I tracked my units, and by the time I got to the end of my step 4, I'm seeing newtons over kilograms. So I know in my mind I'm doing something right, because I know in my mind that a newton divided by a kilogram is a meter per second squared. Now that might be a little bit more obvious to me than to some of you. I'm not assuming that's obvious, but I am assuming it's true. Like F net equals ma. You all, many of you told me that in the chat. Force units equal mass units times acceleration units, right? Like literally. So what is a newton of force? It is a kilogram of mass times a meter per second squared of acceleration. So when I got to that last step, I mean, and again, if I'm saying that too fast, let me know, or play the tape again. But in that last step, where I have acceleration equals newtons over kilograms, I now know I haven't messed up. It looks good. Like I'm doing something right here. So in my final answer, I could be like, do the math. I get A equals negative 100 meters per second squared, which it should be for acceleration. Now, also note that I got a negative. I got a negative. That is correct. It is also important. It is required. In fact, people always ask, like, what if I left the negative off? Well, I'll tell you this. At the beginning of the problem, when we did the diagram and fact pattern, it was our job to label the diagram with coordinate axes. It is our job. It is part of the physicist's way of doing things, necessary way of doing it. You have to make choices about what constitutes positive and what constitutes negative. We have to make a choice. We didn't have to make that one, but we have to make a choice. Why did I make that one? Well, because, for example, the problem told me that the initial position was 0.15 meters. The problem didn't say that the initial position was negative 0.15 meters. I mean, I could make it that, but I like to have as few negative signs as possible. So I just went with the most convenient, straightforward thing and decided, okay, where that thing starts off, I'm calling that positive. I think that's why you don't have to, but I think it's like the most convenient, wise thing to do. So, but if that original position was positive 0.15, then I do have to say here and now that to get an actual fully correct, like full correct answer to the final step here, we should be getting a negative answer. Because and maybe this would be a time where if this were an exam or something, someone might even put in English right there, like, thus, at this moment, the mass is accelerating to the left. That's what this that's what this means, that the mass is accelerating in a leftward direction. Let me slow down that for a second and say, you might want to put in your notes, I don't yell a lot today. I'm not, I hope it's clear, I'm not angry at anybody. I mean, if anything, maybe I'm angry at students from 15 years ago that made error, but I'm not, I'm just like intense. I hope it's clear I'm not angry at anybody. I'm just trying to like probably warn you of errors not to make. That negative sign means negative acceleration. That means acceleration in the negative direction. It doesn't mean slowing down. That's really what I'm trying to say here. It does mean something. If it weren't there, it would be wrong. If you didn't have that negative sign, then we're implying that this mass is about to accelerate to the right, which is bizarre because we need to recognize if the mass has been pulled to the right, the spring is trying to restore it to the left. We need to know that. But so the negative has to be there, but don't think it means slowing down. It doesn't. It means, in this case, speeding up in that direction. That'll come up later in the problem. I hope that's clear. Okay. I'm just looking at the chat. Okay. Oh. Yeah. Question, Takura. Good question. I'm still working on pronouncing your name. I'm sorry, but good question. Do you have to track? Okay, good question. You definitely want to track the units, yes. Now, whenever they literally cancel out, please do show. If there's more thoughts that you, okay, yeah, maybe I didn't show enough detail here. You're saying maybe, like, I guess maybe I would put off in the court. Like, they don't literally cancel out, right? Like, it's not like a literal cancellation, but it is that 1 Newton divided by a kilogram does equal a meter per second squared. So maybe you want a little explanation off to write something like 1 Newton. No, sorry. Spelling that like. I think this is a very good question because so you could write something like what I just did in the side. You could. I'm not literally saying you have to, but you could. I am certainly saying you're going to see, and I think we saw earlier in the other, like when units literally cancel out, like up here at the top, yeah, like up here, they literally cancel out, and I showed that, right? Like newtons per meter canceled out with meters, so I canceled them and we have newtons. So yes, please do show when they cancel out. I'm thinking that right here, they're not literally canceling out, but something's happening. So you want to make it clear. And so in a way, the reason I like Takurub's question is that in a way, and other people are asking, in a way, what he's asking is like, how much do we really need to show? Like how small do you want us to break down our steps into? How detailed do you want us to get? Which is a very fair question. And here's really the answer is no, there's no such thing as too much. The more you can show, the better. Especially if it's an exam. Honestly, here's the standard. The reason we're writing all these steps down is to retrain our mind to see all of these steps clearly one at a time. It's like we're literally trying to slow down the movies of our mind. We really are trying to take our own intelligence and slow it down so that we're more comfortable when our intelligence doesn't seem to be immediately serving us. Like that is really what we're doing here. So the goal is when you're sitting down to do one of these solutions, if you can even visualize a step in your mind, like Takurub's question, if you're starting to write things down and in your mind, you even go like, oh wait, does he really want me to show that the units are canceling here? If you even ask that question, then the answer is yes. If you could even, and literally, not sarcastically, if you could even visualize what the step is, put the step down. You'll be doing everybody a favor by doing that. The worst thing you're doing is taking more time to write, but I apologize for that. There's not that much work in this class, really. You're just putting a little bit more effort in. But the point is, you're just putting in the effort of transcribing the thought that you just had. I'm not asking you to think more. I'm asking you to put your thoughts on the paper. So anything that occurs to you as a possible step, put it down. No step is too small. The idea here is to break everything down into as many small steps as possible, especially on the exam, because you're going to find on the exam, it's open book, it's take home, it's open internet, it's share with friends. And I'm not kidding. So what could I possibly judge you on? I can't just score it on whether you get the right answers or not, because everybody will have the right answers from the start. The only possible way I can judge whether your work is good or not is the more you show me that you really understand what you're doing. So that's the habit we're trying to get into here. So yes, if you could see a way to show that the units cancel, show it. The one last thing I'm going to say about this, I know I'm saying wait, but whatever, you try to write the way I speak, okay? And we'll make a deal. If the more you can write the way I speak, the less I'll speak this way, if that makes sense. Because the moral of the story is there's two different scenarios ever. There's two different scenarios where you should go to extra special effort to include extra special more steps. Two scenarios. One scenario is where you really understand it. You really know this crap and you really want to show me that. Well, then go to town and just write everything that you understand and use different colors and make arrows and have comment. Like the more you actually think you get the material, write more. Show me that you really get it. That's scenario one. The other scenario where you should write a lot of extra steps is when you don't feel that you understand the material. The more rocky and insecure you feel, the more you're like, then the more you should write down whatever you do know or whatever you're thinking, the more process you should give, because you're going to give me that much more room to be generous in the grading and help you help yourself. So when you really understand, write a lot. And when you really don't understand, write a lot. Okay. Okay. Yes, someone in the chat has asked me to pick up the pace and answer these questions. And he asked it in a very, or she asked, someone asked in a very polite way. So yes, thank you. And you should put that in, you could count that for points of, please go forward. Yes, I'll pick up the pace right now. Thank you for asking me that in a way that I don't feel totally, okay, so question 3. Is at, I believe it's at x equals 0. Stop me if I'm wrong. I'm gonna just keep writing if I'm not. And again, I'm assuming, is this the right one? Step 3 is same as before. But I think that's a totally reasonable request. So I believe if this is correct, maybe just confirm in the chat if I just do the right question, just confirm that somebody. But if this is the correct, is that a yeah? Okay, is that a, if this is the correct question, then there's a blast through those steps. At x equals 0, acceleration is a different value now. It's just notice same GDP, same procedure, different answer because we're asking about the acceleration at a different spot. At equilibrium, the acceleration is 0. Oh, we're about to be quickly interrupted by my caveman son. I apologize in advance. He's going to interrupt in a caveman way, and then it'll be over, and we're going to keep going. But I'm just going to silently write one note about that answer. I'm going to move on. Note. In brackets, this is like a teacher note. You don't have, well, whatever. If you put this in your homework, it'll be fine. But note, definition of equilibrium. I will say this as quickly as I can, but I want you to note when the mass is moving it, right? We let it go from x equals 0.15 meters, and it's racing in toward the equilibrium position. It's going faster and faster and faster as it moves. Why? How do I know? Because it's accelerating, right? So it's accelerating toward the center. It's moving faster and faster as it goes. By the time it gets to the center, it really has a lot of speed. In fact, we're going to ask in the very next question, what is its speed? It's going to be an answer that's not zero. Okay, it's moving when it gets to the equilibrium position. It's moving at the equilibrium. So what I just want to quickly bring to your attention is when people think of equilibrium, they tend to unconsciously think, oh, rest. They think things have, sometimes people think things can't move at equilibrium. That is not what equilibrium means. Things can move. Things can have velocity at an equilibrium. What they can't have, by definition, is acceleration. What equilibrium means is all the forces are balanced, or the net force is zero. Therefore, at what equilibrium means is you're not changing your velocity. It means that if you are sitting there, you'll continue to sit there. That's what makes it equilibrium. If something's placed at equilibrium, it will never spontaneously leave it, okay? But the definition of equilibrium is place where instantaneous acceleration equals zero, not necessarily velocity. Okay, that's what I have to say about that one. I'm going to move on. Okay. What is the interruption, maybe? All right, so now we're on question 4. Yes, now it gets a little more tricky. I can see why someone wanted me to pick up the pace. And this ends at 5. This ends at 5. This ends at 3:05 to 5.
45.
Okay, thank you. Yes, thank you. And I apologize. And again, thank you. And because I'm really interested, because I'm sort of psyched that someone asked me to speed up, so I will. But therefore, also, if anybody who needs to take a break, like I won't know, and I won't be insulted. Just take your break and then come back. Like I'm going to keep going. I'm not. If I could finish this fast enough, 5 minutes early or 10 minutes early, I'll let you go early. But I'm just going to keep going because I'm really kind of happy that one person had the guts to ask that. So it's important feedback. So, all right. So question 4. So I'm not giving you a break. So take a break if you need it. So question 4 is now at x equals 0. This is a much harder question. I'm still going to move a little bit, but still, okay. Hopefully you've gotten used to the fact that for step 1, I just keep saying, all right, step 1 of 2. Step 3. All right. I'm going to come to the chase here. I want you to put an asterisk here. I'm deliberately, again, in order to honor, because just like I say, in order to honor the fact that I'm sure it's not only one person here who wants me to get on with it, in order to honor that, I'm going to give you the GDP right now. I'm going to like kind of blast through this, but I want you to put an asterisk here because I think it'll be very fair at some point for people to ask me a bunch of questions about this, or at some point I either might need or should need to expand and back up and sort of tell you where some of these things are coming from that I'm about to write down. But in theory, they come from Physics 101. Okay, so in theory, you know them, but really, I don't want us to fool ourselves and pretend we know them just because in theory you do. So I'm going to just do stuff right now as though it's clear to everybody, but put a reminder here that you're allowed and encouraged to ask me about this later, whether it's at the end of today's class or next week. Okay, but here we go. I think the GDP. Well, here's the GDP. First thing I'm doing this real quickly. My first GDP that I'm writing, I'm actually writing. I'm writing things that aren't true. I'm saying, first of all, hey, the force at any given spot does not equal the original force. I mean, that's a short saying F does not equal F naught is a physicist's way of saying the force isn't constant here, apparently. Like F equals negative kx. It's changing from x to x. We sort of just realized in the first three questions because it's a spring. I'm not saying that's always true in physics, but okay. So for a spring, the force is changing. Oh, and this is it. And therefore, the acceleration is changing. The acceleration and the force are not constant. In fact, I'll even be more specific. I'll say the force seems to be some function of position. It's changing from position to position because this is a spring. Therefore, the first general statement that I'm making is I cannot, for this map, like F net equals MA is true. Like it's always true. And I used it for the first three questions, but it ain't going to help me at all now to say F equals MA or to say something like X equals 1F AT squared or any of that stuff because I don't have a constant A anymore. The first three questions asked me about one particular spot or another particular spot, but now it's asking me, uh, it's asking me to get the velocity. It's asking me to get velocity at a certain spot. But if I try to use any of my old equations that relate velocity to acceleration, they'll be true, but they won't help me here because I don't know what acceleration to use anymore. The thing's moving through a bunch of spots. Okay. So quick thing I'm saying is part of the issue, this is a harder question to know what to put down to use, but part of the way we figure out what to use as our GDP is we write down things that we can't use. That will guide us to realize what we can use. So I'm saying the key point here is acceleration is not constant. Force is not constant. Force depends on position. Therefore, I'm going to use the model or the equations that I always use when force depends on position. First, I'm going to write it as an equation. a lot of English. I'm going to still try to keep the pace going here. I'm going to read the English, and then I'm going to turn it. So again, this statement right here. It would be very legitimate if a lot of you had a lot of questions about this statement. Like, we may need to circle back and talk about exactly what I mean by work or exactly what I mean by conservative and all that. I'm not going to do that now because I'm trying to whatever. But I will say this is my GDP. Okay, I will do. What work approximately equals is force times displacement, right? Work is force times displacement. So when forces change from displacement to displacement, that's generally the time that we start thinking about work and energy. Okay, that's just like a reminder up there in the bracket. But the key point here is that when you have a system that all the forces doing work on it are so-called conservative forces, then that system will conserve mechanical energy. The total mechanical energy of the system will be a constant from any one position to any other position. That's a truism. That's a GDP. When this condition is met, that is true. I will add also side two, and you could, in theory, this is part of the GDP. We're going to get more to the details of how there's certain forces known as conservative, others that are known as non-conservative. Conservative forces include gravity, elasticity, universal gravity. So gravity at the surface of the Earth, gravity anywhere in outer space, the spring force, and the electrostatic force, the Coulomb force, which you might not yet recognize from physics, but you might remember from chemistry, but also will come up later in this physics course. Those forces, how do I know, like, why are those forces conservative? Any forces that have anything to do with equilibrium, any forces that try to get something from one place to, like, gravity is always trying to bring you to the ground, spring forces are always trying to bring you to the center, protons are always trying to bring electrons toward them, masses are always trying to bring other masses toward them. Any force where there's like a clear sort of equilibrium state or preferred state or ground state, those are known as conservative. All the other forces, contact forces like tension, friction, normal, those are not conservative. So why did I just say all that? Just to say here, to get here, only force doing work is the spring force, and that is conservative. Thus, oh, sorry, I can leave that for a second. Sorry. The GDP that I'm about to write down. So the GDP that I wrote in English, because again, it's been a long time since you've thought about this idea. Like we haven't said anything about work or energy or anything in this class yet. And I don't even know that you said that much about it in lab. But in English, what I'm saying is, as long as you know that all the forces doing work are conservative on a system, then the system will maintain a constant total, a constant amount of what we call total mechanical energy from any one spot to any other spot. Now, let me give you the details of that mathematically. Mathematically, and tell me if you want me to go back. E, capital E stands for total What that is, by definition, is the sum at any given spot in position. Total mechanical energy at any given position. What that means is the total amount of kinetic energy plus the total amount of potential energy at any given position. That's what E will stand for from now on. Like that's what if I say total mechanical energy, I mean all of your kinetic and all of your potential. Skip some steps or whatever. So, okay, that's like, system. I'm writing a lot here, and you would too. If this were literally your exam, and we literally had just gone from question 3 to question 4, you would write a bunch for question 4 because question 4 is a big leap. It just is a big leap. We're into a new topic now. Now then for the rest, like question 5 is totally based on question 4. You wouldn't write all this again, right? But we do have to sort of justify why we're going into a whole new concept now, which is energy. We're going into a whole new concept because the question's forcing us to, because we no longer can rely on acceleration or force directly to answer it, okay? So I have to be explaining a lot to you, and you would have to be explaining a lot to me. Not in exactly these words, but okay, but I think these are like the minimum of what would be necessary to motivate this next step for the first time. Once it's established, then all the rest you can just refer back to it. Okay, so thus for any conservative system, what I'm saying is x equals 0 must equal ke plus pe at any other spot such as x equals x naught. This is my GDP. That was my step 3. I'm now going to apply it in step 4 to this particular problem. Back. So, I'm going to go on. Tell me if you want me to go back. I'm totally fine with that. Okay. E equals 1/2 mv squared. That's always true at this stage of physics. I mean, it's always true in classical physics. I think you learned it in physics 101. Put an asterisk. Right now I'm going to accept it as a truism for the sake of today's class. Put a star if you want to text me about that, or if next week in the chat you want to go back to that and say, well, where did that come from again? I think that would be perfectly fair, and you should not be ashamed. But for the moment, I'm saying, but I will tell you, it's always true in this class, and in what, like, it'll never not be true that kinetic energy is 1/2 of the mass of something times the square of its speed. Energy is a little bit more, actually, potential energy is a lot more complicated. But I'm going to try my best right here to condense and say, here, G in this case equals spring potential energy. Like I have to say that, right? Because potential energy can come in different forms. There can be potential energy due to gravity. There could be potential energy due to a spring. There could be potential energy due to the electrostatic force. In fact, the whole idea is anytime any conservative for any force that's ever trying to bring you somewhere, we always talk about how if you're not there where it's trying to bring you, if gravity tries to bring you to the ground, if you're anywhere but the ground, we say that you're storing up the energy that you'll gain when you eventually hit the ground. That the whole idea of potential energy is that it's the energy that's stored due to the work that a and you might want to write this down. I'll just say it again. Potential energy, general, is the energy that is stored potential energy in general is stored energy how much energy will be gained once a conservative force has done enough work restore a system to equilibrium. I will say that again, because this is across the board true, and it's true in English, and it justifies like where all these other expressions are going to come from. Potential energy in general is stored energy. It is the amount, it is a prediction of the amount of energy that will be gained. A conservative force has done enough work to restore a system to equilibrium. Okay, and again, if you want to specifically ask me to repeat that, I will. Otherwise, obviously, you can play the tape again, et cetera, et cetera. But the thing I'm trying to drum in right now is potential energy is something that's only associated with conservative forces, but it is associated with all conservative forces. It has everything to do with the fact that conservative forces try to bring us back to equilibrium. And in order we bring things away from equilibrium, we had to do work against the conservative force to do that. So we tell ourselves that that work that we do against the conservative force gets stored and gets saved up until it gets restored when the system brings itself back to equilibrium. It doesn't apply to friction or tension or anything that doesn't ever try to bring things back to equilibrium. So anyway, the potential energy in this case is the potential energy stored by the spring potential energy. In spring potential energy, for the moment, I'm going to say what it is 1/2 kx squared, where k is the stiffness of the spring. Again, I guess for the moment, I'm saying that's true. I think I could say a lot more about why that's true, but for the moment, I'm going to say that is true. Its spring potential energy is 1/2 kx squared. Thus, yeah, definitely put an asterisk if you want to ask me about that. Thus, here, we say KE plus PE at it is, okay, 1/2 mv squared plus 1/2 kx squared mv squared plus 1/2 kx squared at x equals x naught. Notice how this thing works, and I'm going to flip the page in a second, but what we're always, when we use energy conservation, we use energy conservation when we know the speed at one spot and we want to know the speed at another spot, or vice versa. Like we know the spot at one speed and we want to know the spot at another speed. But it's a speed to spot correspondence. Like literally, that's what mechanical energy conservation is all about. It's a speed to spot correspondence. So we know the speed at spot x equals naught, x equals x naught. So that's why that's my whole right side. We're looking for the speed at x equals 0. So that's my whole left side. The whole idea is that the total is always the same. So we compare a spot that we know the total to a spot where we're trying to find the total. That's what I'm doing here. Okay, so I'm just going to rewrite on the next page. I'm just recopying. So we have 1/2 mv squared plus 1/2 kx squared. Recopied, right? Now notice, some of you might want to start plugging in numbers now. This is a case where I highly encourage don't plug in numbers until we simplify and algebraically manipulate and all that. Like, let's do all the algebraic simplification and manipulation we can. And we're in step 4 here, right? This is all step 4, yeah. So the first thing I'm going to do, I think this is kind of like what Takarub asked before. Like, I can factor out a 1/2 from both sides and divide both sides by 1/2. So I can cross out the 1/2s, right? Then I can start rearranging. Like, what am I trying to solve for? I'm trying to solve for this thing right here. I'm trying to solve for the V at x equals 0. My whole assumption here is I know everything else. I do. Like, the reason I'm using this equation is I know everything else. Before I start plugging in the hard numbers and the particular numbers, like simplifications that I can. So 1 half mv squared at x equals 0 plus 1 half kx squared at x equals 0. Well, when x equals 0, x equals 0. So on this side, that x equals 0, this whole thing goes 0. So I can cross out that whole term. Right? So this whole thing is going to cancel out. Similarly, on the other side, when x equals x naught, that's not the same as 0. Like x naught is not the same as 0. But when x equals x naught, we were told at the beginning of the problem that v, when x equals x naught, in other words, that initial displacement of 15 centimeters, it was held at rest there. V equaled 0 there. So that whole term, right? You have to understand that these two different sides of the equation are referring to two different positions in the system. We're comparing two different positions. So at each position, all the values are different. But at one position, really what I'm saying in English is at equilibrium, the left side is this left side is talking about the equilibrium position. The equilibrium position, the potential energy is nothing. There's no potential at equilibrium. That's the whole definition of potential energy. You store potential energy to get back to equilibrium. So at the equilibrium position, there's no potential energy. And at the turning point, at the outside initial point of this whole motion, there's no kinetic energy, right? So what I'm left with, if I'm doing the algebra here, I'm left with saying, okay, 1 half mv squared at x equals 0. Not even 1 half, because I already crossed out the 1 half, so I guess. Equals 1 half kx squared equals x naught, right? Now, you see what I'm saying? So, more clearly. And I want you to, I'm watching the clock, I promise. We are making a lot of progress here, I think. Notice this, it looks like 1 half mv squared equals 1 half kx squared. One thing I have to emphasize to all of you is this took a lot of work to get to this step, a lot of work. This step, 1 half mv squared equals 1 half kx squared, that is not a GDP. Everybody thinks it is. People think it's some kind of law that kinetic equals potential. It's not a law. It is not in general true. You'll see in the next question, we're going to do it fast. The next question, we're going to do a lot of the same concepts. We're not going to say that kinetic equals potential. There's no law that says all kinetic and potential must be equal at any point. What this is saying is, or what we're always saying is, the total amount of energy over here at any one spot must equal the total amount of energy over there at one spot. We happen to have picked two special points for this question. One point where all the kinetic disappears, and the other point where all the potential disappears. So what we're saying here in English is all the kinetic at equilibrium must equal all the potential at the end point, the amplitude point. That's what's equal. It's not that they're both equal at some given point. It's that the kinetic at one point is equal to the potential at another point. I'm just saying, okay, hopefully that, so it's not a GDP. It's the result of all of, it's not a thing to memorize. It's just a result that happens to apply in this particular circumstance. It's a big difference between step 3 and step 4, but okay, that's what I have. I'm just still looking at the chat. Okay, so now I can solve. We're solving for v squared equals kx, and I'm plugging in now. By x, I mean x naught on that right side, equals kx squared over m, right? Therefore, v equals square root of kx naught squared all over m, right? And again, notice I haven't put any numbers in. I've like isolated the v as though this is an algebra problem or something. V is what I'm looking for. It's going to be equal to all that. So I'm going to go to the next page. So equals 200.15 squared all over 0.3, right? And if you do that on a calculator, I'm going to cut to the chase here and say for step 5, at approximately because I'm doing a square root, right? equals 3.87, or it might be 3.78, but I think, I think it's 3.87. Correct me if I'm wrong. I think it's 3.87. You could do it on the calculator. That is the answer. I'm going to keep going. That's the answer to step 4. Obviously, stop me if you want to. That's to step 4, to question 4. And by the way, I'm intentionally not, I don't have any illusion of doing the very last question today. That actually was never on the table. You'll see why next week, but so I'm going to keep going. We'll get to everything but the last question. So question 5. I believe, is per second. Where did that happen? Like, what is X, right? I believe, again, stop me if I'm wrong, but I believe that's the question for question 5. At when we're at V equals 3 meters per second, what is X? Okay, so the GDP, we can cut to the chase here. Step 3 GDP. Here is exactly the same as last time. This is important. This question actually is designed to get at like the essence of a GDP. The GDP is the same situation, right? We still have the mass on the spring. All the forces doing work on the mass are still the same. They're all conservative, and it's the same type of question. We're just flipping the information. Last time we asked, when the mass is at this spot, what is its speed? Now we're asking, when it has this speed, what is its spot? It's literally the same idea, just we're inverting the information. So the GDP is absolutely the same. The GDP is 1F mv squared, and you could skip straight to this stage net. Like if this were to exam or whatever, you've already explained all this above. So it's already established now. Same thing as before, but notice I'm doing, and you could say something like, in this principle, see above, right? It's okay. Now, just notice the one subtlety. Now, what we always are doing with conservation of energy, I always, whenever someone says, I know the speed here, what's the spot? Or, you know what I'm saying? Whenever it's a speed spot thing, speed spot correspondence, position, velocity correspondence, I always do conservation of mechanical energy. So you're always comparing, you're always saying the total amount of energy at any known position is the same as at any position that you're solving for, okay? So this time we're not solving for X equals 0. That's what we were solving for last question. We've solved for that now. Now we're solving for a particular X, like which X? We don't know. That's what we're solving for. We're solving for what is X when V equals 3. So the unknown spot is literally X. Like that's literally what I'm trying to find out. What am I comparing it to? Well, I'm going to compare it to the same thing I did before, the equilibrium, the X naught, the initial position, because that worked last time. For the record, now that we figure everything out about the equilibrium, I could just as easily compare it to that. It's fine, whatever you want, but you compare it to something you know. So, okay, so there's my GDP. Now I start filling it in for. And what's going to happen is I'm going to finish this. It's going to be 5:30. We have 15 minutes. What I'm going to do then is literally, I'm going to write down the answers. I'm going to skip all the steps and everything because I think you get the idea of the steps now. Once I finish this semi-hard question, for the rest of the questions, I'm literally going to write down the answers so that we're all on the same page and we've all seen it and we've made progress. And any questions you want to ask, you can ask next time. And the meat of what we're going to get to next time is the very last bit. But anyway, that's what I'm going to do just so we have closure. You've all been very patient as usual. Step 4, PAW, here we go. Well, first of all, I can divide out all those halves just like I did last time. Okay, when x equals x, I'm looking for zeros, just like I did last time. When x equals x, is v equal to 0? Well, no, v equals 3. That's the condition of the problem. So I can't cross out that first term. When x equals x, does x equal 0? No, it equals x. That's what we're looking for. So I can't cross out anything on the left side, is my point. I cannot cross out anything on the left side. On the right side, can I cross anything out? Oh, yes, I can. When x equals x, when x equals 0, then x equals 0. So sure, I can cross this out on the right side because x equals 0. Fine. So, but now, very important subtlety is I can only cross out one term. So notice right here, I am not going to be able to say 1f squared equals 1fkx squared. That's not a thing. That just happened to be a thing for the last question. Here, so what am I solving for? I'm solving for x. So I'm going to arrange algebraically. I'm going to say, okay, I'm going to isolate the term I want. Kx squared mv squared when x equals 0 minus, I'm subtracting from the other side. I'm subtracting mv squared, mv squared when x equals x. Do you see what I'm doing? I'm isolating the kx squared from the left. I'm subtracting 1f mv squared from both sides. But be careful. Like you might think, well, wait a minute. You're subtracting one, so you have 1f mv. The halves have already canceled out. So you might be thinking, wait, mv squared minus mv squared on the right side, isn't that 0? Well, it would be 0 if they were the same v's, but they're not the same v's. They're v's. When I start plugging in numbers in a moment, you'll see that. Also, you might think, oh, wait, can you cancel out an m from both? No, I can't. If there was an m in every single term, if there was an m on the left side as well, I could cancel it out, but there isn't. So I can't cancel out the m. So I'm just going to keep doing algebra here for a second. I'm looking for x, right? I'm trying to solve for x. So I'm going to say x squared equals mv squared when x equals 0 minus mv squared when x equals x. That's what I have for all over k. That's what I have so far. Okay, now I'm going to the next. X squared equals mv squared when x equals 0 minus mv squared when x equals. Okay, I believe this one just equals. Nonsense. Well, x equals 0, we figured out in the last question, right? It's 3.87 squared, right? You could factor out, but you can't divide out at the end. M is 0.3. V when x equals x, when x equals x, what the heck does that mean? That's the condition of this problem. It's asking us to solve for x when v second, right? I mean, it was told to us you should check, but it's told to us in the problem. So it's 3. So one of the v's is 3.87 and the other v is 3, and that's all over 200. If you do that properly, I'm cutting to the chase because I'm looking at the clock. If you do that properly out on a calculator, you will find that the final answer, well, here, okay, I'm going to go to the next. Tell me if you need me to go back. But on the next page,
Oh, Professor, really quickly, do you mind just going back to that so I can take a screenshot?
No, absolutely. I'm sorry. No, I was hoping someone, I think it was crazy if no one said that. Yes, please.
No,
please.
thank you so much. Thank you so much. Wonderful.
All right, thank you. Awesome. Okay. And sorry I jumped too. I'm kind of a jumpy guy. Okay. No, I'm glad people are still awake out there. Okay, so you got it. You're good. You're good. By the way?
Yep.
Okay, and you're good. Okay, awesome. Okay, so here's my final answer. At v equals 3, x. I just already did this on a calculator, obviously. Like I know, but you should check on a calculator or whatever. I mean, I couldn't do this in my head. Don't think that. But you would get something like, so the answer you get, if you do this correctly, is approximately 0.095 meters. That's just a number. I mean, I couldn't have predicted that, but it's true. But how do I know that number is at least reasonable? Because it's between 0 and 0.15. If I gotten a number that's bigger than 0.15, something would be really weird. How do I know that? Because the thing was speeding up from 0 continuously to 3.87 meters per second. And the question asked us, when does it have a speed of 3? Like 3 is like somewhere in between 0 and 3.87. So for this question to make any sense, I had to get some kind of position that was between the maximum and 0. And I did. Like that doesn't prove I'm right. It just proves that I'm not crazily wrong. Okay, that's the answer to that. Now I know again, you guys are being very patient. I'm going to now quickly, I'm going to switch my screen, pardon me. My screen so that I can just sort of bust through the answers of there. And I think most of these next questions, except for the very last one, which we're going to talk about for the rest of our lives, I promise, for good or for bad. The rest of these questions are, are they're more like thought questions anyway. So that was 5. All right, so I'm turning the page. So I'm not even going to write the step method now because we have 10 minutes. I'm just going to write answers so that you can know if you're understanding or not. So question 6 was like, how far will the mass compress the spring once the mass is instantaneously stopped and about to reverse direction? Like how far will it go on the other side? Well, if all of this is true, if we're really assuming well-behaved spring and conservation of energy and all that, it will go to the same distance on the other side. It'll go to x equals it'll go to x equals negative 0.15 meters. Like that's the answer to question 6. If you thought that, you're right. So now we're just trying to make sure that we have a kind of an intuition of what the situation would look like if it's a really, really good conditions. The better the conditions are, the more it will look like this. The worse the conditions are, the more it will stray from this. But you can get conditions that are good enough that it'll look like this to a measurable extent. So assuming that the amount of friction is too small to make a measurable difference, how many indistinguishable cycles can this mass complete until it's incapable of moving? The answer is infinity. Like, again, that's optimal. Like, but if the spring is as good as this problem is saying, if we can really believe that all mechanical energy is being conserved, then what we believe now is that the spring would start at the 0.15, it will zoom in, getting faster and faster and faster, gets to the equilibrium position, then starts slowing, going down until it runs out of that same amount of energy. And of course, if it's gonna run out of energy, if it's going to run out of all of its kinetic energy and build up the exact same amount of potential energy that it ever had to begin with, it'll land at the same spot on the other side that it ever began with. And you can check it with the math. Like it's 1/2 kx squared plus 1/2 mv squared. Again, it's just that there's 2 different values of x squared, a negative value and a positive value. So it's going to go from 0.15 to negative 0.15 and go back and forth forever, is to the extent that the spring is ideal. So the answer is forever, infinite cycles. And that's what we're assuming of this. Then 8. Okay, I'm going to say this quickly. We might want to think about this more next time, but it asks, like, so in the first quadrant, like just when it's going from x equals x naught in to x equals 0, just for that first fourth of a cycle of motion, asks what's happening to the magnitude of each of these quantities. So first it asks what's happening to the speed. The speed, like magnitude of velocity, is known as speed. The speed, how do I know? It starts at 0, and we just said at equilibrium it ends up at 3.87. So the speed is increasing as it goes in. Another way I know is it's accelerating. It's accelerating in the negative direction while it moves in the negative direction. So it's gaining speed from 0 to 3.87. So the thing is speeding up on its way in. Then it asks, what's the acceleration doing? Now, this is a little bit interesting. This thing is accelerating. It is speeding up, but acceleration is not the same thing as speed. If you look at the numbers and you look at the facts, at the beginning, the thing was pulled really at the outside at x equals x naught. It's pulled really hard by a restoring spring force. It's pulled in with a force, if you look back, of like negative of 30 newtons magnitude. And it's accelerating at, therefore, this really high rate of magnitude of like 100 meters per second squared. So it starts racing it. So it's racing in at that acceleration rate. It's getting faster and faster and faster in speed. By the time it gets to the equilibrium position, it's built up all of this speed, but it has lost all of its acceleration. Its acceleration is now down to 0. Now, you really might want to make a mark on that in your notes. Like, I really want to say this is a hugely important point. Half of you may be like, duh, yes, obviously, but half of you may one third of you might be like, yeah, duh. One third of you might be like, wait, what? Did you just say that the speed went up while the acceleration went down? Yes, I did. And one third of you might not be thinking anything and might not think that's a problem, but maybe you should think about it because it is interesting. I am saying, so you can ask me next time, but what I'm saying is the speed went up while the acceleration went down. How can you visualize that? What I'm saying is it's gaining speed the whole way on its way in. It's getting faster and faster, but by smaller and smaller chunks, right? Like first it gains like 10 meters per, or like 0.2 meters per second of speed. Then it only gains 0.1. Then it only gains 0.05. Then it only gains 0.01. You see what I'm saying? It's gaining speed on the way in, but at a lesser and lesser rate until it gets to the equilibrium position where it has a maximum speed, but no acceleration at all. So it's not going to gain speed anymore. So now it starts moving the other way, slowing down. You follow what I'm saying? Well, either way, it's true. Then it asks this very weird question. It asks, what about the jerk? Well, the jerk should stop talking in 4 minutes for everybody's sake. But what does it mean by jerk in physics? It means the rate of change of the rate of change of position with respect to time. Who's anybody ever asked me that before? How am I supposed to know? Good question. Let's see if there's a pattern. Notice I know I have 4 minutes left. We're almost there. Notice I asked for speed and it was going up. Then I asked for, so speed is like the change in position, right? And it's going up. Then I asked for the change in that and it's going down. If I want to see if there's a pattern, why don't I back up for a second and ask a question that maybe the question should have asked me? What if I just ask, what about the position itself? What about the position itself, the magnitude? It started at 0.15 and it moved into a position of 0. The position went down, right? I mean, I'm not saying that's tricky or surprising, but I'm just saying it's a fact that might help me with a pattern. The position went up. The rate of change of position went down. The rate of change of that went backwards. Sorry. The position goes down from 0.15 to 0. Remember, I'm only talking about magnitudes here. Don't worry about negative or positive signs for this question. The position went from 0.15 to 0. That's down. The speed went from 0 to 3.87. That's up. The acceleration went from 100 to 0. That's down. So if you just look at this pattern of rates of change, they're going down, up, down. If I had to guess what the next thing in the pattern would be, I would guess up. And by the way, that's correct. I'm speaking quickly now just so we can sort of satisfy everybody in the class as best as we can. You can ask me any questions you want about it. Also, you remember you can resubmit based on any of this help that I've just given now. No, it's not your issue. Wait. Hold on.
We hear you now.
Oh, you do? Okay. And it wasn't you, it was me, my iPhone or whatever. Okay. My AirPod cut out, so I had to put in another one. Okay. Sorry. So look, I know we have 1 minute now. What I just want to do, bear with me for 1 minute. I might go like 30 seconds over, but I really think we're in a great place. I think we've made major progress. One important question, someone just asked in the chat, I don't know if you heard my answer. Someone asked, is there a deadline to resubmit 1B? There's no deadline. If you got anything out of this class and you can do better on 1B, please do it. There's no deadline, like until I say otherwise. That's number one. Number two, someone said, can I explain jerk again? Fair question. By jerk, I mean the rate of change of acceleration. I can explain that in more depth next time. If you know calculus, which some of you do, I mean the third derivative. If acceleration is the second derivative and if velocity is the first, I mean the third. If you don't know calculus, I just mean an analogy. Jerk is to acceleration as acceleration is to speed. If that's not good enough, I still understand, but I'm gonna try again next week with you. Just remember that for next week, okay, to ask me again, because I know we're kind of out of time and there's just one last thing, because I appreciate that someone sort of like forced me to get through this sheet, someone helped me get through the sheet. I want to give you one last answer. The answer for the very last question is the thing that you've been working on in lab. Now, I need to really break it down and really explain it and give you my perspective next time. But you've had enough perspective from me. Bear with me. If you have to go right now, you have to go. But if you can wait for like 1 more minute, let me just write down the answer to question 9 so you can at least know if you're in the ballpark or not. And the answer sort of comes from what you've been doing in lab. The answer for question 9 is you've got to use this thing that I think you just tested 2 days ago. I think it was one of your, or something like it, was one of your 3 things that you were and also I know there was issues with Desmos where 2 things seemed like they both could be right, and it wasn't clear how to distinguish between one. We'll have that whole discussion next time. Believe me, I know. But I'll tell you right now, for closure, this is ultimately the lecture version of the thing that you maybe could have or will be getting out of lab from the last lab. This is what but I'll explain it in depth next time, but you would plug in literally this. Because the question 9 is at t equals 1 second. What is x? Very hard question. It's the point of the first 3 labs, okay? I'm not pretending to explain why this is right now, but I am saying it's true. And I am promising you that I'll explain it. But if you do this, and if you're in radian mode, you must, when you plug these numbers into a calculator, which you have to, no one can do this in their head. The calculator has to be in radian mode. Please, has to be. But if you do that, you will get that the answer is approximately 0.116 meters. So just that's the answer that's definitely the hardest question in the whole sheet. There's no way anybody could get it without like 3 labs and a lot of thought and a lot more explanation next time. But at least we're now sort of caught up to where we are. Okay, and I think I really appreciate it's such different feedback from such different types of people. And some people told me to slow down, some speed up. I really appreciate it. I think it made for a very balanced class. I hope you think so too. I hope you can get the information you need from rewatching the video or whatever. You should go. You should have a good night. I will see you next week. I'll stay in touch with your instructor. I will turn off the recording, and anybody who wants to hang out and ask questions certainly can. Okay, thank you. Have a good weekend.
Thank you.
Thank you. Thank you very much.